start here, or is that because of the delay?
There's going to be a small delay, but then it'll...
Ah, okay.
So they can probably be starting now.
Oh, okay. How do you change things on this screen? Like the way to scroll through the chat? Oh, okay. Okay, we'll get started in a few minutes. Just wait a bit. Oh, what's the attendance form? Oh, okay. Hey. Okay, for everyone online, we'll start in a few minutes. We just have some people coming in, so we'll get started soon. Cool, okay. Can everyone, just a mic check, can everyone hear me? Cool, okay. I think we'll get started. Hello to those of you watching online. My name is Hassan, and I will be running the 3106 crash course. Firstly, it's nice to see all of you here, so thank you for coming. I hope that you can get something out of this, and that includes everyone watching this at home. Just to give you a bit of outline of how this will run. So for the first 10 to 15 minutes, I'll give some exam advice, how to best prepare for the exam, how to study for the exam, and things you should be avoiding, and also some tips as to how to approach design questions. And then I'm going to explain a few different things which people have asked me to explain. So things like watchdogs, so a lot of the week 10 content, so watchdogs, FMEA, which I can't remember what it stands for, but it's like failure something mode analysis, I can't remember. That's also week 10 content. I'll talk about power amplifiers, oscillators, and also setup and hold time of digital gates. So that's just a bit of content at the beginning. And then I've picked out 3 questions from final exams. So if we have a look at a standard final exam, so maybe a full, so what we're looking at here is essentially the 2024 full paper. So your exam will be the exact same, so it'll be 75 marks, 3 questions, which are split into 25 marks each. And what you'll be given at the start of each paper is going to be a data sheet, and that's going to pertain to 1 or more questions, generally just 1 question, but it'll make it very clear in the question what this refers to. Hello. And each question, so this is, for instance, question 1. So it's going to have 5 parts, and they're all of equal weighting. So even though one question of these 5 parts might be more difficult, you can just skip it and go to the next question, right? Often what Torsten will do for each of these questions, if you can't answer, say, part A, but part B needs the result from part A, he'll just say, assume this, and then that's the result you'll use. So for instance, you can see in this question, it says, in the following, it is assumed that. So if you get stuck in a question, feel free to just move on. There's never going to be a carry forward. You're never going to get stuck in that sort of situation. Now, in terms of the questions I've chosen, so I've chosen question 1 from 2024. So that's a differential amplifier sort of question. The second question I chose was a transmission line based problem. And again, the questions I picked were what I thought most people were struggling with, at least what I found a little bit difficult at the time. So there's a lot of design questions. There's a design question at the end, which will be good to go through. And then I picked from 2023 a question on power amplifiers. And the last 2 questions are a little tricky. So I felt that they would be good to go through. There's also some stuff on batteries, LDOs. And when I get to these questions, I'm not really just going to be giving solutions in a sense. And what I'm going to be doing is explaining what each of those core elements are. So what the LDO is, what the power amplifier is, and I'm going to go through each little step, which is really how you should be approaching these questions, right? So if you're getting stuck with a question, the first thing to do is to go back to the system. So for instance, in this system, what we see is that there is an LDO, a core system, and that thing at the end is a power amplifier. We'll come back to this, so I'm not solving it now. But if you're struggling to understand how this system works, the first thing you have to ask yourself is, how do these individual components work? So how does the LDO work? How does the power amplifier work? How does the battery discharge profile work? Only once you've understood them, then you go back to the question. Now, in terms of how you should be studying for these exams, so you have about a week left, which is plenty of time to study, hopefully. Although I understand there's also tele and EMAG right after, which is unfortunate. But if it's any consolation, when I was doing electronics, I was very nervous for this exam. This is probably the most nervous I had been for an exam. So if you're feeling nervous, that's completely normal. But probably the thing I wish someone had told me when I was studying electronics was how to study the past papers properly. So what you have, so this is not the past paper, but like let's pretend this is your past paper. Now, in previous courses, you might have been able to get away with memorizing. Now, hopefully, you've understood that from the style of the way Torsten runs this course is that memorizing will not work. If you try to memorize, you may as well sign up for next year's course offering. In the nicest way possible. You are going to struggle, right? And that's because Torsten does not recycle questions, right? If you look on his website, he's uploaded all the way from 2011, all the way up to 2020, what is it this year, 2025. That's about 13, 14 past papers. And people still fail the course, right? And what that essentially means, it's really quality over quantity in terms of how you approach these past papers. So when you have a past paper, you set a 2-hour time limit. So if it's after 2017, the exams are 2 hours. If it's before 2017, the exams were 3 hours. I think, right, semesters were 2017? Yeah, so it would have been before pre-2017. And you set those that 2-hour time limit, and you force yourself to put something down for every question without looking at the solutions. The second you look at the solution, you've nullified the difficulty of the question, right? Because the hardest part with these questions is finding the correct pathway to pursue. The second someone sort of nudges you in the right direction, you think to yourself, oh, that's so easy, right? I would have figured that out. But it gives you a false set of confidence, because really the difficulty, again, is nudging yourself in that right direction, getting that intuition to find the right direction. And that is really hard, right? It's going to feel super uncomfortable for the first few papers, because you're mostly going to be itching for a solution the second you get stuck. But you have to do everything you can not to look at a solution, right? And even if after those 2 hours you can't write something down, you force yourself to put anything down, even if it's garbage, right? You just need to let your brain do something, right? And I don't mean to sound mean, but really you have to force your brain to do something. It's like if you go to the gym and you try and deadlift 300 kilos for the first time. It's not going to work, right? You need to work up at it. You need to deadlift 10 kilos, then 30 kilos, and 50 kilos, right? You can't expect to walk in and be able to solve a lot of these questions freely. But what you'll notice is after a few papers, if you start approaching them correctly, and you start trying to do them yourself without looking at the solutions, you start to notice you can start to answer questions by yourself, right? And that's the key component, because again, there are no recycled questions in these papers. You will not find similarities. I mean, maybe there's some Enigma code Torsten uses, I don't know. No one's been able to crack it thus far, right? Maybe you can be the first one, but I wouldn't recommend spending your week trying to figure that out, okay? So, was there any questions on any of this? So I just really, if you're going to take anything away from this crash course, it's this, right? How you approach the past papers. Don't just try and do as many as possible. Try and do them to as high a quality as possible, right? Someone who does 5 good past papers and studies the content well and understands the content well does better than someone who does 20 past papers. Okay? Yeah, was there any questions on any of that? As to the structure of how the exams will run, anything. I should mention, someone was asking me about what you should be taking into the exam. I've seen some pretty comical things. So it's an open book exam, and I've seen some people take things like the Cedra and Smith textbook. Now that's about, what, 1,500 pages. Please don't do that. You're not going to end up using it. Really, it should just be as a refresher for things. So if you just need a quick refresher on something, like how does a differential amplifier work, you have that ready to go in your notes. It should not be for on-the-go studying in the exam. Okay? I can promise you could print out all the past papers. It's not going to help. Right? People have tried. I mean, I was one of the people that tried. Right? I printed them out. I didn't end up looking at them once. And it wasn't even because maybe they could have helped me, but there were just so many questions, and those 2 hours start to feel very overwhelming when you're like scribbling through all your past papers and all your notes trying to find the correct solution, right? Often for most of these questions, the solution is very simple, right? But it's getting to that solution that is difficult. That's hopefully what I'm going to try and show you. I'm going to show you my thought process behind these questions, how I approach these questions, because the solutions are online. You can have a look at the solutions if you want. So yeah, cool. If there was nothing else, I think I'd get into the content. Cool. All right, so now, what I've heard is that week 10 content, one of the lectures was skipped. Is that correct? Okay, so what I aim to briefly explain are some of what I think are the key components, what will probably show up in the exam, or what has a high likelihood of showing up. So generally, week 10 is concerned with, if I have a system, how can I analyze the errors that may arise from this system? So the first thing we'll look at is a watchdog. So a watchdog. So a watchdog in English is just, you have a system that's going to run for 10 seconds, right? That system, let's say it transmits a 1 over 10 seconds. What we have in a watchdog is a counter. So a counter, and you write this counter from some code, I don't know, flip-flops or something. And this is all happening in a microcontroller. Okay, so you write some code that'll count. And let's say it counts for 10 seconds. This will then go into a NAND gate. And you have a signal from your system. So this is a signal from system. And we'll look at the output. So this signal is, so again, your system has run for 10 seconds. And if the code, after counting 10 seconds, let's say emits a 1, then I expect the signal from my system to also emit a 1 after these 10 seconds, right? If it emits a 1, what's the output of the NAND gate? 0. So everything is good in that case, right? So it's counted up to 10 seconds, and it's seen that after 10 seconds, the system has also emitted a 1, so nothing has gone wrong. But if the system emits a 1 after 10 seconds, and the signal hasn't yet transmitted that signal, so if there's a 0, what would the output be? 1. So then this tells the system that something is wrong. So then this signal then gets sent back to the system. So you can imagine your system is something like this. And it sends a reset. And it just resets the system. So the system was supposed to run for 10 seconds, but it hasn't, something has gone wrong, so it resets it, or sometimes just shuts it off. Okay? And this is all happening in the context of a microcontroller. Okay, the system's not in the microcontroller, but you get the point, right? Now, this is essentially how a watchdog will work, and a question in the exam will likely be phrased on, we have a system, it runs for this long, and it transmits this signal. What is set up a watchdog to test if this system has worked, right? And the difficulty in that question usually comes up from setting. So sometimes what you're going to need in your system is some sort of timing diagram. You're going to need some sort of timing system, right? So you're going to need some timing system which after 10 seconds, because we're checking this every 10 seconds, after 10 seconds, takes a signal from the system and sends it to the watchdog. Okay? That's generally what a question would be. Is there any questions to this? I think the overall concept is okay. It's just sometimes implementing this can be a little difficult. From memory, there are a few past paper questions on this. But that's the general approach. Okay? Something else. So okay, the next thing to cover would be FMEA, which again, I can't remember what it stands for. I think it's failure methods and error analysis. Can someone fact check that? I can't remember. Is that right? Maybe. Okay, so this is another similar sort of system of just we want to test how robust our system is. So essentially, you have a system with a bunch of components, and we look at each component. Yes? Oh, mode. Thank you. I've been fact checked. Mode. Oh, I'm the worst. And is that effect? Okay. Yeah, okay. There we go. So failure mode and effect analysis. So generally we're going to have a system, and we want to test what happens if this component if something goes wrong with this component. What is the effect on that system? And generally it's on an individual component level. So you can imagine an amplifier with a few resistors or a capacitor. The question then is, what happens if this capacitor shorts? Or what if this capacitor opens? And that's how the past paper questions will be framed as well. So you have a system maybe you haven't seen before. What happens if this capacitor goes open or short circuit? So an example would be, let's say you have a Schmitt trigger oscillator. So something like this. Like this. See? And so we're familiar with how this works. So the Schmitt trigger has levels and hysteresis. This capacitor is going to charge up and discharge, which is going to flip it between the hysteresis levels, which generates the square wave. Now, the question might be, what happens if this capacitor, if something goes wrong? So what if this shorts? What if this capacitor shorts? What happens?
The out will always be 1.
Yeah, so the first... Yeah. So if we short this, so if we imagine this is shorted, then what we can see is that the input is always pulled to ground. So there's no more charging, discharging, and the input to the Schmitt trigger is always going to be low. The output depends on whether it's inverting or non-inverting. And then you could also conversely look at what happens if it's open. So if I open this, so if something goes wrong and it opens, what would happen? Otto?
It depends on the output purely.
Depends on the output? In what sense?
So there's not going to be any current going through the resistor, so voltage levels input equals output, right?
Yeah. That's true. Input equals output, yeah. Yep.
That depends on how the Schmitt trigger is built. Most likely what's going to happen is going to oscillate and wave frequency dependent on the propagation delay of the Schmitt trigger.
Yep. You're both correct. So if when it comes to questions like this, if you had put either answer on the past paper, you'd likely get the marks. Okay? That's probably something else I should mention. If you look at Torsten's papers, they say suggested solutions. A lot of these are very open to interpretation. So as long as you give your interpretation of a question, or you have a different method, you can still get full marks, right? It's not like that's the only solution. Okay? Does this make sense so far? So we're just testing things. Another good example would be, bear with me while I draw this. So if I have a bridge rectifier, yeah, okay, it's not.
It's not bridge rectifier.
Yeah.
It's a hidden mixer.
No, but not yet. And then bear with me. And then resistor, capacitor. Oh, sorry, not ground. And then these will connect. Oh, that isn't. I always suck at drawing this one. That is awful. But okay, so this is a bridge rectifier, right? It's not. What have I drawn wrong?
Yeah, it's a hidden mixer. Your diodes all in the same direction.
Yeah, that's right.
One should be one direction, the other should be in the other direction.
Yeah, that's right. Yeah, it's just gonna go in the wrong. Yeah, okay. Anyway, yeah, the diode's in the wrong direction. I don't feel like drawing it again. The point is we know how this works, right? I just wanted to draw it as a symbol. You are correct. I have drawn it in the wrong direction. But we know that this rectifies, right? So what will happen and how the rectification works, assuming I've drawn it correctly, is that in one direction, so in whether the signal is, so if you have at your input, something which oscillates. So in this case, it's positive, and in this case, it's negative. Whether it's positive or negative, current is going to flow into the resistor at the same direction, right? Now, a question might be, in terms of failure mode and effect analysis, is what happens if one of these diodes goes wrong? What happens if one of them, I don't know, if something happens? What would happen? Would it stop working? So what if this diode stopped working? Would it work? It would still work? Who said it would still work? That's correct. Who said that? Good. Yes, you're correct. It would still work. And what would it work as now? Yeah, half-wave rectifier. Again, assuming it's drawn correctly, half-wave rectifier, because one of the parts is now broken. And that's another example of a question you could be given. Okay, it's really circuit dependent, so it's going to depend on whatever circuit you're given. Does that make sense? Good. Okay. The other thing which I think is important from week 10 content is, and again, this is something which I can't remember the name of. Maybe error check or something. Error check. I don't know. Error check. Yeah, it's probably not right. But anyway, let's assume you have a system composed of a bunch of amplifiers or something. It can be anything, right? Resistor doesn't really matter. I mean, I don't know. Anything, some system. Now, generally when you have a PCB, right, or you have a package, you only have access to a finite number of pins, right? So you can imagine your input and output might be one pin, right? So input, output, but then you might also want pins around the circuit. So you might want a pin which checks what this voltage is, what this voltage is, what this voltage is. But again, you only have so many pins that you can actually probe on a PCB, right? Your design manager might say, okay, I'm allocating you 3 pins on the PCB, right? That means you have to get creative with how you test errors in the system, right? Because if something goes wrong, and I haven't put in built-in like a probe system on the PCB, I can't easily just probe it, right? Especially if it's in packaged and with shielding, right? So one thing we can do, so you can imagine if I want to take this, and I want to take this, and I want to take this. So these aren't my input or output, but they're just parts in my system that if something goes wrong, I want to be able to check if one of these has gone wrong. What we can do is we can then put these into a mux, like this. Like that. I did not think this through. Okay. So you can put this into a mux. And now what we know with a mux is that you can actually essentially select which one of these you'd like, right? So you can imagine as the number of these grow, let's say I have 10 points I'd like to probe, I can't just get 10 pins magically out of nowhere, right, on my packaged PCB, right? You have a finite number that you can have access to. So what then what comes out is then one output. So you select what you want to look at, right? And then you send it into an ADC, and then into a microcontroller, like that. Okay? So this would be, the S would essentially be a pin on your PCB, or your packaged PCB. So a pin there, and then you'd also have a pin here. So you'd have one pin here and one pin here. So 2 pins, as opposed to having to need 10 pins for all these different things I want to check. Does that make sense? So this is generally how it's done. Because again, everything is easy when your design manager tells you, okay, you have 50 pins to use. In reality, you're only given like 3 or 4, right? So you have to get creative. And generally, on chips, we always do this sort of thing. Is that clear? Any questions? Yeah? Oh, nothing. It's sorry. You mean these stages up here? Oh, the ones. Okay, yeah, the one up there is rubbish. So okay, so out of the mux comes a signal, right? But that signal might be analog, right? So what we do is then we convert it to digital, and we look at what happens on a microcontroller, right? That's just purely for simplicity in some senses. Yep.
For the FMEA.
Yep, this one.
How do you actually see how the error is? Like when you open the capacitor, how do you know it's not gonna what effect it has?
Okay, that's a good question. So really, you start with how does the system work, right? So in the case of a Schmidt trigger, we know how the Schmidt trigger works, right? And you have to look at, so when we're looking at the FMEA analysis, we're looking at a specific component, right? So for instance, this capacitor. And the first question we ask ourselves is, what was this capacitor's function in the circuit, right? This capacitor's function in the circuit was to essentially charge and discharge the input, which then swings it between hysteresis levels, right? That's how we know what will happen if the capacitor shorts or grounds, because we know what its original function was. And then you split it into 2 cases, what happens if it shorts and what happens if it opens. In terms of like a fast and hard rule, I don't think there is one with this one, unfortunately, because this one is really circuit dependent on what happens when something goes wrong with this capacitor, right?
What about the diode one?
So with the diode one, now the diode one, so this one here, I've drawn it wrong, that's a caveat, but what we can see is that for the positive and negative path, so the positive path, it'll take, so 2 diodes are responsible for the positive part of the signal, and 2 diodes are responsible for the negative part of the signal, right? And so my question was, what happens if one of the diodes breaks? So for instance, if this diode breaks in the system, right? But if 2 diodes are responsible for each path, what would happen if one of them breaks? Only one. So let's say in the discharging path, one of the diodes break. Would the positive path still work? So we have 2 diodes responsible for the positive part of the signal, and 2 diodes responsible for the negative part of the signal. Right? When one of the diodes breaks in the negative part of the circuit, it doesn't affect what's happening in the positive side, right? The positive part. So there's 2 parts in the circuit. When one of the diodes breaks in the second part of the circuit, it doesn't affect what happens in the part of the circuit that's responsible for the positive signal. That sort of makes sense. I think this one does require practice. A good exercise for this one is go to circuits that you've already learned and just ask yourself what happens for different components. That's likely what a question is going to be.
So you can't say half negative.
Yeah, so exactly, half-wave rectifier. Exactly. So we say it still works, but as a half-wave rectifier now.
But the positive doesn't change.
Yeah, exactly. Does that make sense? Cool. In terms of other content from week 10, there's stuff like the statistics and all that of the failure rates. I don't think that's super complicated, so I'll probably leave that. Does anyone want me to talk about things like electromigration? Do we want to hear about electromigration? Maybe not. Yeah, I don't think those are too critical for your exam. Probably what I want to move to next is oscillators. Did anyone have any questions before? Cool. So, any questions? Okay, so oscillators. Now, the difficulty with oscillators is the ones you've been looking out in say 2133, they're quite intuitive and easy to understand in some senses. So you have generally something which starts it up, and then the oscillation will continue. Like we think back to, I don't know, 2133 lab 3, right? Or lab 2 or something. The oscillator had a clear charging and discharging path, and we essentially picked that frequency by changing the capacitor values, right? Those were more obvious oscillators. The oscillators in this course are what we call filter-based oscillators, okay? So generally what it'll look like is you have some square wave, like this, and then this will get sent into a bandpass filter. And what the bandpass filter is going to do is it's going to pick apart one frequency from this square wave. Because we know a square wave is composed of harmonics, right? So that would be the first harmonic, that would be the second harmonic, the first and third harmonic, sorry, because the even one skipped. And what this bandpass filter is going to do, it's going to select that one frequency, right? It's going to select that fundamental frequency. So what's going to be the output is some sort of thing, and this is fed back, right? So like this. This is fed back into something which saturates. How to draw this? Something like that. So okay. So this is just a saturation block, right? You can think of like an amplifier's feedback or something. And then this goes back. Now this is self-sustaining. So what will happen is you can imagine the amplifier or the inverter will clip, and then it will be sent to a bandpass filter, and that signal will then come back, and it will just keep going around and around and around and around. Now, as to how these start themselves, right? Generally, in reality, what there is noise. So noise will get amplified, and that'll start the oscillation, right? So getting oscillators to be self-starting isn't always trivial. It's not always easy. But generally what we do is we start it, because we know for oscillators, we have that the loop gain around the circuit has to be 1. Sometimes what we do is we start it up greater than 1. So we start up the oscillation. It's like you're starting a lawnmower. We start it really fast. And then once the lawnmower starts, We don't have to keep yanking it, because it's just going to work, right? Now, this is a bit abstract, so I think maybe it's best looked at through an example you've seen in the lectures. But the criterion for oscillations are that the loop gain is 1 and that the phase shift is 360 degrees or 0 degrees. Now, the reason it needs to be 360 degrees is so that the signal comes back to its original form, right? If the signal was, say, 180-degree phase shift, it would look something like this. So that's the signal, and then that's the signal that returns back. And you can see when we add these two signals, what's going to happen? They'll just cancel each other out. That's why we need a 360-degree phase shift. Okay? So what I'll look at is a Pierce oscillator. So a Pierce oscillator looks like this. Now, what we have generally is a resistor in the feedback path, but I'll come back to that, right? That is a critical component, but just to keep it a little simple at the moment. So when we analyze what this crystal is doing, so let's have a look at this crystal. So this crystal has an inductor. And so crystals are essentially like, it's like a piezoelectric system, right? So there's mechanical vibrations of this crystal. So that bottom, the inductor, capacitor, and resistor is essentially the inertia of the crystal. That just, I don't know, for interest, it's not too critical. Now, what is really important about this crystal is its properties of what happens when we look at the input and the output. So you can imagine if I have an input to the crystal and an output to the crystal, it has a very selective behavior. So it has a sort of very selective bandpass behavior with a high quality factor. So this is like if I drew frequency versus V out over V in. So what we can see is that at one particular frequency, F naught, the resistance, the crystal is essentially like a piece of wire in this part, right? Everywhere outside of this filter, of this frequency, it's not allowing any signals through. So it's like an open circuit, right? So if I'm here, remember that the inductor and capacitors will essentially resonate each other out. I am skipping a few details, but they'll essentially resonate each other out, and we're just left with a small resistance like this. So that's what it'll look like when I'm at resonance. Outside of resonance, so somewhere here, it's going to be an open circuit, like that. Now, why this is important is because if I look back at my Pierce oscillator, what I can see is that that crystal is only ever going to, so that inverter loop is only ever going to have a feedback loop at what frequency? The resonance frequency. Because what happens outside the resonance frequency? What does this crystal look like outside of resonance? Open circuit. So is there going to be a feedback loop? No, right? So what we can see is that there's only ever going to be a feedback loop established at that one particular frequency, right? Which is how we get an extremely selective frequency. Does that make sense so far? Good. Now, the other key, so this is C1, C2. Before we actually get into how it now oscillates, the other key component we usually have is a resistor that sits here. And this resistor is usually like a mega ohm. So it's usually quite a large resistor. And this is essentially just for biasing the transistor. But what does biasing mean? So we know that that inverter is just a simple CMOS inverter, so nothing too crazy. And we know what the voltage transfer characteristics look like for an inverter. That's not great. But so this would be input versus output. So when the input is low, the output is high. When the input is high, the output is low. Right? Now, at what point, where is V in equals V out? Because that's essentially what I'm doing for this, right? This is my input, and this is my output. So what's happening here? So when I connect these resistors, what am I doing? So again, this is before the circuit's even on, right? How am I biasing it? V in equals what? V out, right? On this curve, where is V in equals V out? Yeah? So say it again? Yeah, in the middle, right? Right here. So right here. right there. So that's where V in equals V out. Now this might be a little unusual to, so this is the biasing point by default. So before any oscillations happen, this is where we're saying we want the biasing to be happening, right? So the system is going to sit in the middle by default rather than left or right. But as we know with this transition region, it's extremely steep. So what happens if there's a bit of noise, here? What happens? So you can imagine, I've turned it on, I'm sitting at this middle point, and then there's a bit of noise. Where does it flick? Left or right? It's probably right because we're adding noise, but because you can see how steep it is, right? It only requires the most minuscule of pushes, right, at the input to go to the right and to go to this point here. So I'm sitting here. So this is my input. This is where it's biased by default. Then I get a bit of an input, and it pushes it this way. And if I push even a bit this way, I fall, like that. Does that make sense so far? The one thing I'll add is, if you have any questions, please stop me at any point. The only use in this is if you're learning something. I mean, I'm having fun, but like, only if you guys are really learning something, okay? And I can promise you no one is going to remember the question you ask in like 5 minutes, right? If you're nervous, no one will remember, right? So feel free to ask anything, okay? And I might get something wrong, so yeah.
So you basically stabilize that point?
Stabilize what, sorry?
That point right there.
In the middle? Yeah, essentially, that's like the default biasing point of the thing. So it's an inverter, it's a digital logic, but we're using it like a linear amplifier, right? Just to get this started, okay? And then what happens when I turn this on? So this inverter will give me minus 180 degree phase shift. What about these capacitors? What is the total phase shift from these capacitors? So how much phase shift do I get from one capacitor? 90 degrees, and then 2 capacitors gives me 180 degrees, right? So all up, what's the phase shift something going through that loop will experience? Negative 360, right? No trick questions, I promise. Maybe later, but not now. So yeah, so negative 360 degrees, yes.
Should we always label it as like 360, or would it be alright to label it as a 0 degree?
0 degrees works as well, but in this oscillator, it's 360 degrees. There is a case of an oscillator where it is a 0 degree phase shift, and that would be the Wien-Bridge oscillator. I'll talk about that right after, okay? So yeah, so it can either be 0 degrees or 360 degrees, it just happens in this case it's 360 degrees. And obviously there's a very mathematical way of doing all of this. It's a little boring, but hopefully you can kind of see how this works now. So you have an input that essentially starts up, so we default it at the middle of that transfer characteristic. So a little noise flicks it on. Then that signal essentially gets saturated, and then it goes through the feedback loop, right? And it experiences a negative 360 degree phase shift. But not only that, right? So we can imagine what's happening at the output here. So it's getting a little messy. But because it's the output of an inverter, we know it's flicking back and forth, right? Let's just assume it's flicked back and forth, right? Now, when this goes through that filter, what happens? Which frequency does it select? It's going to pick one frequency. And so as I mentioned up above here, somewhere, it's essentially a filter that filters, so it goes around the system, and it filters it here into a sine wave. Again, I've skipped quite a few details, but it does get a little complex. But hopefully that gives you a little intuition as to how these oscillators work. They're always going to look like this, right? They're going to have some sort of gain element, some sort of nonlinear element, and they're going to have some sort of feedback loop with a filter in them. That's all of the oscillators you'll ever see that are like this. Was there any questions? Again, yeah?
What is this called again?
This is the Pierce oscillator. Pierce oscillator. Now, a similar oscillator, just to drive home this point, a similar oscillator you would have seen, what does this look like? I think it's like capacitor, inductor, capacitor, inductor. So this would be the Wien-Bridge oscillator you would have seen. Is this correct? Can someone fact check this on me? I can't remember if this is what it looks like. I think this is correct. I think it doesn't matter anyway. Because what I'm concerned with is this, what are these 4 components doing, right? Forgetting about the oscillator for a second, right? This is the Wien-Bridge oscillator. So Wien-Bridge. Now, what this is this here is a low-pass filter, and this is a high-pass filter. So that is high-pass, that is low-pass. And so what do they make combined? What type of filter? Bandpass. It's the same thing, right, as what we just had in the Pierce oscillator case. Again, it's another filter in the feedback loop that's going to pick one frequency. And that's the frequency this oscillator is going to run at. Now, in this case, back to your point, Otto, this is something which has a 0-degree phase shift, right? So at this particular frequency, so what we see is that there's inductive and capacitive elements, and at the resonance frequency, we know that the phase shift is going to be 0, purely just from this filter. Again, ignoring everything else, we're just looking at this filter. Yes. Online question. Will the capacitor C2 not be slowing? Sorry, I just saw this question. Okay, so we have a good question. So would this capacitor C2 not be slowing the square wave? Was that in reference to the Pierce oscillator? Okay. Due to having to charge to the output impedance of the inverter, which would be a small time constant, but nonetheless. Okay, so with the capacitor C2, so this capacitor, due to having to charge through the output impedance of the inverter, output impedance, so you mean this impedance? So just to clarify, do you mean this impedance? Yeah, that's okay. So okay, so the question is essentially, this C2, would it not be slowing the square wave? And due to having to charge through the output impedance of the inverter, which be a small time constant, but nonetheless, maybe. So I think I see your point. So you're right. So it might, but generally we, I wouldn't say it's too significant of a problem. Generally we tune it such that that isn't a problem. So this does require tuning. No, the output of the inverter, which be small. Yeah, I see your point. Yeah, so there would be some output impedance of this inverter, because the inverter has to be pulled high or pulled low, and to get to high or low, it has to go through essentially a transistor which has resistance. Yeah, so it would be, but it wouldn't be enough to affect it, I'd say. Yeah, generally they're quite small. Yep.
Could you remind me where the 360 comes from?
The 360, yeah, sure. Okay, so essentially we're looking at a signal, and we're looking at what happens as it goes through the loop. Right? So a signal starts here, and it goes like this. That's okay so far? Now, we look at all the phase shifts it undergoes as it goes around. So the first phase shift comes from the inverter, which flips it. Then we get another phase shift from the capacitor C2, which is minus 90 degrees, and then another phase shift from this capacitor C1, which is another minus 90 degrees. And all up, what we get is minus 360 degrees.
No, I mean you wrote minus 360, minus 180.
Oh, no. My apologies.
Oh, okay. That's what I was
Yeah, that's separate. Yeah. Okay, no extra phase shift. Is that clear so far?
Yeah, that's clear.
Cool. Now, the very last thing I'd like to look at, so again, we will get into the questions so close, but the questions won't take too long. The next thing I'd like to get into is power amplifiers. And there is a question we're going to go through on this, but I'll just explain the theory. And again, there's a lot of math associated with this. One of the questions we're going to go through has some math involved. What I want to go through is just an intuitive way of understanding the different stages of operation. So generally your amplifier, so any transistor you work with is a power amplifier, right? So what we generally have is, let's say, VDD. And again, just pretending there's no actual oscillating input signal, I just want to think about how do we actually turn this transistor on, right? So if I have some input signal here, and again, I've also obviously emitted resistors and all that. We're just focusing on the transistor for a second. Now, what are the two conditions to turn on a transistor? NMOS. So a PMOS would have a little bubble here, like that. What's the condition to turn this on? So the first condition is that we have to apply a positive enough gate voltage to turn this on, right? Because remember, the channel in NMOS is full of negative charges, right? N-doped MOSFET. So that means we have to apply a very positive charge at the input to attract those electrons up and form a channel from here to here, right? So when we look at the first condition, so what I want to look at is the drain current. So that's the current flowing through. So again, we're assuming, So there's another condition which says that the V drain source must be greater than the gate. We're just assuming that's fine, right? That's not the important condition. That's not very hard to fully satisfy in power amplifiers. And it doesn't really explain the different stages, okay? The different stages are dependent on the first condition, right? So if I plot the gate source voltage against drain current, sorry, other way around actually. So if I plot the drain current as a function of gate source, now, what would the gate source voltage be in this case? Yeah, so it would be so you're both right. So V gate minus V source, but the source is here. Now the source we always consider an NMOS as the lowest potential because, again, the channel is full of negative charges. Again, this is just semantics and definitions. And obviously the lower potential, or where the negative charges come from, is ground, right? It's not going to come from the power supply. So we consider this as the source of negative charges. So V in minus V source would be 0. So then this is just V in. And the way I like to think about these transistors, okay, I'll draw how it turns on. So it turns on like this. And it turns on at some threshold point. And that point you see up there, that's just the current limit of the MOSFET. It can only output so much current, right? So we see two nonlinear regimes. We see at the beginning where the threshold voltage is, and then we see at the output where the saturation occurs of the MOSFET. Sorry, saturation is a bad word. The current limit of the MOSFET. Now, the best way to think about the power amplifier is to imagine it like a valve, right? So from this region, right, you can imagine you're trying to turn the valve, but there's a lot of friction. So you have to put in you have to turn it a lot before you actually see something come out of the sprout, right? Like, let's imagine it's water. You turn it a little, there's still no water, then all of a sudden at some point water starts flowing, right? And the more I increase, the more I twist that valve, the more water that flows, okay? So class A operation sits in the middle here. So class A. So what we can see with class A is that by default, so again, this is before you put in any oscillating input signal. This is just purely biasing the transistor. The way we bias this class A transistor is we bias it such that there's always current flowing through it. So again, back to the valve example, it's like I've turned it halfway and I've left it halfway, right? That's how, by default, I've turned the valve, okay? So what you can see is that, does this make sense so far? Is this okay? Yeah, good. So biasing by default is class A. And then let's imagine, so maybe let me redraw this a little. So you have V in. Now this V in is going to be a combination of V DC plus V AC. Right? So the V DC is what's responsible for getting the transistor into that class A operation. So by default, it's on. So what happens as I start to oscillate? What happens? What do I see at the output? So I take the output here. Again, in the absence of any resistance. Just if I now start to swing this gate voltage, what point does it swing around? The bias point, right? So again, back to the valve example. I've turned it halfway. Now if I start turning it back and forth, right? It started as on. Now I turn it back and forth, so I turn it back, less water, more water. But in both cases, it's still on, right? Even if I left it, it was still on. So you can imagine what's happening as I swing this gate voltage. So maybe now let me draw it here. So the bias point sits here. So this would be your bias point. And then what I'm doing is I'm oscillating it around that bias point. So I'm just swinging this amplifier. So I'm swinging it back and forth and back and forth and back and forth around this bias point, right? And what you can see is that you have to swing it a lot to get it into either of those saturation regimes, right? So I have to swing it a lot this way to go that way and swing it a lot this way before I enter into one of this region or this region up here, right? So that's why class A is generally very linear, because it's always on. It's never off, right? Class A is always on. You have to swing it a hell of a lot to turn it off, right? But what's the efficiency like? Bad, because it's always on, right? I've always left that water running in the tap. Again, so your water bills would be high, not so great. Now, Class B is the opposite. Class B sits here. So that there is class B. So class B sits at that threshold point, and what do we notice about class B? Is it on or off by default? Okay, it's a little above that threshold point, but whatever. Sorry, no, it is sitting on that threshold point. Is it on or off by default? It's off by default, right? But you can see that I'm not starting here, but I'm starting right at that threshold point. So a little bit of signal turns this on, right? Because a little bit of signal will flick it this way, right? But what's the problem with class? So class B is very efficient because it's off by default. What is its problem though? It's very, who said that? Features? Yeah. So correct. So it's very nonlinear because we can see that it essentially flicks between on and off. And the second the signal flicks back this way, I hit into a nonlinear regime, right? As opposed to class A, where no matter whether I went high or low, it was still on and it was still linear, right? But when you're flicking between on and off, that's nonlinear. Okay? And then class AB will sit in the middle between these two. So it's essentially a compromise between the two. So class A had good linearity, class B had poor efficiency, class AB will sit somewhere in the middle. That's really all that differentiates these types of classes. I think this gets overcomplicated quite a lot. I don't think this is where the difficulty, when you're actually building a power amplifier, this is probably one of the simplest parts. The more difficult part is the architecture that surrounds the power amplifier generally, and how to get it to stay in these regimes. Yeah. Was there any questions to any of this?
Can you draw the graph for AB and B?
AB, yeah, sure. So okay, so this was, damn, I should use different colors. Okay, so if I were to draw, I'll do it up here. So class B, so drawing current as a function of voltage. And class B, oh sorry, not current. So class B had how much current by default? What was the bias point? How much current was flowing through it? 0. So you start at 0, and so it flicks like this. And then class AB would be like the bias point is here, right there. And so it would be like, I suck at drawing this. So it's like it's been shifted up, right? So it spends more time on than off, right? And the more you move this bias point up, so if I move this bias point up, I change the class of amplifier, essentially. Because I'm just changing how much current there is by default. Is that okay?
Yeah.
Thus far? Any questions? Now, there is class C. So class C is like somewhere here. Class D is very different. Class D, I think he's gone through that in the lectures, class D? Okay. So class D is the most nonlinear of the amplifiers technically, because class D, so in this analogy I was thinking of it as like a valve. Class D you can think of as a switch, right? It's just acting like a switch, switching off and on. So what you send in is, rather than an AC wave, you send in something that looks like this. Again, one other thing I'll mention is I've just drawn one transistor. Generally when it comes to like class B, class AB, we draw these in like a push-pull configuration. That's just so one transistor handles the positive cycle, one transistor handles the negative cycle. It's really good for thermal management because you don't want one transistor heating up all the time, right? So you have two transistors, it's really good for thermal management. That's why we have the push-pull configuration, also a little more efficient. But you can technically run these with one transistor, okay? But for class D, you probably need two transistors, but again, it doesn't take the point away. So for class D, you have something which is essentially flicking on and off. That means that the output is also going to be something like a square wave, right? It's also going to be something, so if I take my output, it's also going to be something flicking on and off, except with more power. That's the point of the power amplifier. I'm taking whatever the input is and adding more power to it, right? So class D is always off. There is no biasing to the amplifier. The biasing comes from the input signal, the oscillating input signal, right? Because instead of having a sinusoidally oscillating signal, now we have a square wave, right? And in this portion, and this portion, so this would be off transistor, off, on, off, on, right? And because it's so nonlinear, what we have to do is we take that square wave signal that comes out and we send it into a filter filter. And out comes a sine wave. And that's essentially class D. That's all it is. So class D can be thought of as something where we're sending in now something which is like a flicking of a switch, rather than something which is oscillating around the point. There is no bias point in class D amplifiers. We don't put in a DC voltage because this is enough to flick the transistors on and off. Is that clear so far?
So also the fundamental frequency,
The fundamental frequency?
the sine wave.
Of this one? What do you mean by that?
I think the sine wave that you get from this wave.
Oh, that'll be, so okay, that'll be, that's a little non-trivial, if I'm being quite honest. That really depends on the frequency of the signal you're sending in, and then how much distortion you get from the output. Yeah, I think it just depends on the PWM, because the signal you're sending in technically is a pulse width modulated signal, so it really depends on that. But yeah, you'd do the filter such that you get that specific frequency. Okay, so isn't that the question? Yeah.
So will the exam be like order of the content?
No. I think there is some structure. Like part A will be like, as you'll see, I've picked questions that also follow a sort of structure. Part A is always going to be some sort of amplifier. Part B and part C, questions 2 and 3, it varies quite a lot. I can't give a definitive answer. Yeah, sorry, I wish I could give more help with that. Any other questions? So in terms of the classes, that's all you need to know. The other thing that's probably very important with amplifiers is we do not bias it like this. Does anyone know why this is a bad idea? So why is this a bad idea? So let's say I'm using a BJT. And this is my base to emitter voltage. And this is current. Now, obviously, as you increase the base to emitter voltage, the amount of current will increase. Now, again, forgetting the biasing for a second, what happens when the temperature increases in this system? Yeah, the bias point changes, right? So what will happen is that the base to emitter voltage is going to drop when the temperature increases, right? And then that'll subsequently drop the current based on how much the temperature is increasing. So it's like a feedback loop, right? I think it's, I think this changes like -2 millivolts per Kelvin or something. Is that correct? Like -2 millivolts or something? Something like that, right? So essentially, as the temperature increases, this base to emitter voltage will decrease. And that will essentially control the current, right? Because you can imagine if this was positive, then that means an increase in temperature would increase VBE, which would increase what? Yeah, it increased current, which is not good, right? So there's like a sort of inbuilt feedback mechanism in these transistors. But if I bias it like this, let's say VDC, what's the problem now? So can VBE change? So let's imagine this is grounded. Can VBE change now? No. What's happened?
You fix the bias point, but as the resistor heats up, you are lowering the threshold. So as the resistor heats up, you are pushing more current, which heats it up more, and you're going to turn on away.
Exactly. So what essentially was happening, what I was talking about before was this negative feedback mechanism where the transistor was sort of protecting itself. But now as you put in this bias, you're fixing VBE. You're not allowing the transistor to change anymore. To change its base to emitter voltage, because this source is making sure this stays the same. So then as temperature increases, current increases, power dissipation increases, which then increases temperature again. Temperature increases, current increases, power increases, and you can start to see a positive feedback loop. And we enter what we call thermal runaway, right? Now, thermal runaway is generally, if you've ever been like G14 and you see students building power amplifiers and there's smoke, this is what it's coming from. They don't have good thermal management in their power amplifiers. So when you're doing DP, keep this in mind. You need thermal management, okay? So when we're biasing this, generally what we'll do is we'll bias it with something like a Zener diode. And the reason we bias it with a Zener diode is because the Zener diode is flexible as well. So it'll be something like Or you could use a VBE multiplier, but we'll just leave it as a Zener diode for now. So something like this. Now, what's good about the Zener diode, and again, I haven't drawn it all, but what's good about the Zener diode is it also changes 2 millivolts per Kelvin with temperature, right? The forward voltage across the Zener diode was also minus 2 millivolts per Kelvin. So as the BJT heats up, right, or as temperature increases, both of them now decrease, right? So that means as temperature increases, this will decrease, right? Because the Zener diode is not fixed at a voltage. The Zener diode can vary with voltage. Whereas my DC source before was making sure I sat at 1 voltage all the time, no matter what the temperature was. Is that clear so far? Is that okay with everyone? Any questions? Cool. All right, well, I think that wraps up the content. I did want to go through setup and hold time, but I'll probably get to the questions and come back to it at the end. Unless someone wanted me to go through it now, we can just jump into the questions. Okay, cool. We'll do the first question, and then we'll have like a bit of a break. Okay. All right, so let's go through the first question. So, I should make that clear. So this is this one is from 2024, question 1. So the questions I'm going to go through, I kind of deleted the cover page. So this is question 1, 2024. The second question I took from 2017, and the third question I took from 2020. So I just went through and I took different questions from different papers. Okay, but I took question 1 from one paper, question 2, and question 3. There is a lot to unpack here. So I'm probably going to go through it how I would go through a question which is a little overwhelming like this. So let's read it. Figure 1a shows a model for a sensor which generates a small signal IS, which again is picked up by an instrumentation amplifier. So the signal they're referring to would be this signal here. So we have essentially a differential sensor which picks up these two signals here. And then it's sent into this instrumentation amplifier, that thing there. The sensor outputs have a substantial unwanted common mode signal modeled by VCM. So that's this thing here. Common mode signal just essentially means to both inputs we send in the same common signal, right? 5 volts at the top, 5 volts at the bottom. And with any sort of differential amplifier, it's supposed to be measuring the difference between the two signals, right? If the common mode gain is really high, is that good or bad? 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 Is the consensus bad? Bad, good. So because these are differential amplifiers, we want them to be amplifying the difference between the two signals. If it's amplifying what's common between the two signals, then it's not doing what we want it to do, right? So then, the next part. So sensor interface is powered from a single-ended supply voltage VCC. The INA826 output voltage is referred to the signal ground reference, VSG. So that would be down here. That's the reference. A partial data sheet for the INA826 can be found at the beginning of this exam paper. Some known circuit parameters are shown in figure 1b. So the data sheet it was referring to was, so this is what you'll be given in the exam. So you'll be given this sort of data sheet. My recommendation in reading time is don't just skip this data sheet. Give it a bit of a read, right? Because you might think that the data sheet is straightforward, but sometimes it can be quite hard to figure out what's happening. So go to the question, and then try to find what you're looking for on the data sheet so you don't waste too much time when you're actually supposed to be writing. Okay. Anyway, back to the question. So maybe just to explain the circuit a little. So if we zoom in. So as I mentioned, the part on the left is the sensor, and this part is the instrumentation amplifier. And that includes R1. But generally when you buy the IC chip for this, it includes everything, but you have to put in an external resistor. That's the only thing you have to put in, besides the power supply voltage, okay? And the reference voltage. And that's just so you can control the gain, right? Because we'd like to be able to control the gain of the amplifier. And as you'll see, what's good about this instrumentation amplifier is by varying R1, you can change the gain. So just by changing one resistor, okay? Now, first question. The instrumentation amplifier must be set to have a differential gain G equals 100. Find R1. What would be the approach here? Yeah.
Like for ease of analysis, you could just split the amplifier into two halves. Like you could just split R1 in the middle and split
That's correct. So I think there's that method. You could also do superposition. I'm going to use a bit of a different method. It's just a method I like, but either of those methods would be valid, right? You just do whatever you feel most comfortable with, okay? And I'm just going to redraw this because it looks a little overwhelming in its current state. So, again, another bear with me while I draw this. So question 1A. So we have a signal, which I'm just going to call V1, and it's sent into an amplifier with a resistance RA. And the output of the first stage, I'm just going to call Vout1. So I'm going to refer to this as Vout1. And then these are joined together by a resistor R1. There's another. Now, what's on the top essentially repeats on the bottom for the other signal. So what you have is another amplifier like, oh, that's horrible. Sorry. You have another amplifier that looks like this. So plus, oh my bad. Minus plus, and then like this. So Vout2. So the way you can really think about this first stage is it's kind of like we're buffering the input signals, right? That's essentially what we're doing. We're sending the input signals into a buffer. Yeah. Oh yes. I scribbled it out, but yes, yeah, it'd blow up otherwise. Good point. Yep. So this is the first stage. Then what we do is we send this in like this, and then we send it into a differential amplifier like this. And the reference signal is technically what's here, but I'm just going to ground it, right? Doesn't really matter for the gain of the amplifier. So, and these resistors are all the same, I think. So really we can split this circuit up into two parts. So the first half, the second half, which is this half, is a differential amplifier, hopefully you've seen before. So it just subtracts this signal from this signal and multiplies it by some gain. But what would the gain of this one be, just looking at it, of the second half? Can I tell straight away, just by looking at it? Why? Yeah, so all the resistors are the same value. So anytime you see an amplifier with resistors the same value, especially, you could go look at the equation, it'll tell you the same thing. But essentially I see all the resistors are the same, so immediately I know the gain of this circuit is 1. So the gain of the circuit is not coming from the second half is not coming from the differential amplifier. So what's the point of the instrumentation amplifier then? So the second half of the circuit isn't actually providing any gain. So what does that tell me the first half is being used for? Or maybe another way of thinking about it is, why don't I just do this? Why don't I just use an instrumentation amplifier to take the difference of a difference amplifier to take the difference of two signals? Sorry? Yeah, so loading from the input or the output? You're not actually wrong, right? So when you have an op-amp, what should the input impedance be? Very high. What is the input impedance if I look, not a number, but like if I look in here and I look at what the input impedance is, what is it? Yeah, roughly 2 times RB. Is that good for an op-amp? Probably not, right? So then you can kind of see the purpose of having this first stage. We're essentially buffering the input signals first, and so the output impedance of those, the input impedance of the circuit is now very high or very low? So the input impedance looking into these terminals. High, right? Which is what we want out of an amplifier. Whereas before what we had, just looking at this one, so what we had is that the impedance looking into the amplifier where my input signals were going to be was very low, which is not good for an amplifier. Right? Was there any questions on that? Cool. Okay, so there's also common mode rejection ratio reasons, but we'll get to that in a second, okay? So how I like to approach this amplifier is, so essentially we need to find what Vout1 and Vout2 are, because the difference is going to be the answer, right? So Vout1, so the current in here is roughly 0, because the current into an op-amp is 0. The current here is roughly 0. And then, what I also know is that because it's an ideal amplifier, V2 is going to appear at the negative input as well of the amplifiers. So that would mean the voltage difference across this resistor is, sorry, other way around, V2 minus V1. That's that. And since I know it's V2 minus V1, which I'm just going to call VD, what would the current through that resistor be? So what would this current be? Yeah, so it's just going to be VD by R1. Now, that current that was here also was here, like that, because there is no current flowing through this op-amp. So this current goes like this, because there's no current flowing into those op-amps. So that means this current, which I'll just call I, is also this current and is also this current. So if I look at the first op-amp for a second, so if I look at this op-amp, like this, plus minus V1, R4, Vout1. Can I find what Vout1 is if I know what the current through R4 is? What could I do? Yeah. Yeah, exactly. Exactly. It's just Ohm's law at this point, because I know what this current is. It's I. So I'm going to have Vout. So I'm going to have V1. So V1, Vout1. So I'm going to V1 minus Vout1 on R4 equals the current, which I just said was VD on R1. Oh, I shouldn't be labeling R4, it's RA. And then I can rearrange this slightly, and I get Vout1 equals V1 minus RA on R1 VD. Was that all okay? I feel like this is just maybe an intuitive way of thinking about the instrumentation amplifier. Then Vout2, so that's first result. Vout2 you can derive doing the exact same thing, just now the polarity is going to be flipped. VD. Okay. Now, as I mentioned, the differential amplifier on the second stage has gain of 1. So if it has a gain of 1, this output here, so Vout, it's just going to be Vout2 minus Vout1. Right? Just because there's gain of 1. Okay? And when you do this, so you subtract this one from this, this one from this one, you get 1 plus, what do you get? It's probably obvious, I'm just slow. You get 1 plus 2RA on R1 multiplied by VD. Yeah. Now we were told what the gain was. So the gain is Vout over VD equals 1 plus 2RA on R1. And this is the gain. And so we know what RA is. We know what the gain is. So you can just rearrange for R1. So then we say, therefore, R1 equals 2RA on G minus 1, which you can just say is approximately 2RA on G, because I mean G is 100 minus 1, it's 99. And then this gives you 500 ohms. And that's the first question done. Oh, any questions? All good? Yeah. You had a question? Yeah, go for it.
This takes so much time to do it here. So if you were to run through, if you were in the exam, how would you jump through the process a little bit quicker?
It's a good question. So how would I jump through this process quicker? Yeah, so this one is, so there are some questions which are going to take a lot of time. As you'll see, there are also questions which aren't going to take a lot of time. So I think the way you handle your time management is in reading time, you go through each subpart, and you can very quickly tell which questions are going to be very long. Like this one, if I have to calculate the gain of an instrumentation amplifier, I know that's a long question. But then if I go look at question C, which is just asking me to find, question B, which is to find the allowable range, I know I just need to look at the data sheet, right? So I think there are some questions you can't get away with it. If there are questions where you can sort of do it a faster approach, I will make that clear. Okay? So next question is find the allowable range for VCM, VCM min, VCM max. As we know with amplifiers, right, they need to there's inside the amplifiers are transistors. Those transistors need to stay in forward active or in saturation, depending on if it's a MOSFET or a BJT. So essentially what this is saying is that there is a limit to what the input can be before we start to send the transistors inside the amplifier off. And this just comes from the data sheet, right? There's no other way we're going to get this but from the data sheet. So if I go up to the data sheet and I look for, so here, so where it says common mode rejection, there's quite a lot of columns, but what you can see is they're split between gains. And what was the gain of our circuit? 100. So the column of interest is, so we're just going to assume 60 hertz. The column of interest is this one here. So what we can see is that it gives us a range from V minus, which is ground, to V plus, which was 3.3. So the range is just going to be 0 to 3.3 minus 1. And that's it.
Where does your assumption come from?
I looked at the next question. But even if you look at this one, you can see it's the exact same anyway. But the next question says use 50 hertz or 60 hertz. Yeah, I probably shouldn't have said use an assumption because it's the same either frequency. What does change on frequency is the common mode rejection ratio. We'll get to that later. Okay. So this means, so for part B, we just saw that the range, so part B, so from the data sheet we saw that at a gain of 100, we have V minus to V plus minus 1 volt, and this is 0 volts, 2.3 volts. And that's it. Nothing else, right? This was a lot shorter than the first question, so some questions are definitely going to take a lot longer than others. Cool. So this is the input range for which your signal, the amplifiers inside the instrumentation amplifier will still behave like instrumentation amplifiers. And we'll get a feel for this actually in question 3 that I'm going to go through. So if it's a little confusing now, because we look at transistors specifically in that question and when they turn off and on. Okay. So next question. So in the following, it is assumed that the common mode signal is 1 volt plus some oscillating sine wave. Find the expected amplitude of the time varying output signal due to VCM. So essentially, it's like in the power amplifier, we had that bias point, and it's just swinging around 1 volt. Now, generally in instrumentation amplifiers, why I mentioned it was good to read the data sheet is because to find the time varying output, so this is part C, so essentially if we block out any other signal, and we're just looking at the common mode signal, so no differences in signals, we're just looking at the common mode signal, what is the gain from the input to the output, right? And then it says, okay, what is the output signal based on that gain? So you'd have to calculate something called the common mode gain, but in differential amplifiers, this is always given on the data sheet. Okay, this is why it's important to read the data sheet early. So then if we go to, so just to make this clear what I mean, so the output due to the common mode signal is equal to the gain, the common mode gain, multiplied by the common mode signal. That's all I mean. And a common mode is given on the data sheet, so we're going to look at the data sheet. Oh, actually, okay, you have to do a bit of work, I forgot. So the common mode signal is essentially going to be the gain divided by the common mode rejection ratio. So what this means, and an intuitive way of thinking about it, is what the common mode rejection ratio just says how good is my amplifier good at rejecting any common signals. A very high common mode rejection ratio is good or bad? Good, right? The higher the better. Ideally, I'd want ACM to be 0, so an infinite rejection ratio. In reality, that's not true. It has a small but prevalent common mode rejection ratio. So again, we go back here. So the common mode rejection ratio, I think it was a 60 hertz or 50 hertz signal, so 60 hertz is close enough. And and we have a gain of 100. And something that most people get confused is do you pick the typical or do you pick the minimum? You always pick the worst case. The worst case for your given scenario. In our case, in our scenario, the worst case is the lower common mode rejection ratio. Because when you design anything, you always design for the worst case situation. So, I mean, I don't know. I think that's a good question for Torsten. I think general practice, just to be safe, is pick the worst case. Always. Now, and what we can see it's either 120 or 130. Worst case would be 120. It's lower. So you would say this is 100 over 120 dB. Obviously, we need to convert this out of dB. For that, you would just do 10 to the power of 1. Yeah. So it's a million. I'm just going to leave that for now. And then this would give you 10 to the minus 4. Okay. So then when we calculate the common mode signal, so if we go back to the question, what do we use? Do we use, what amplitude do we use? What is the amplitude of this signal? Is it 1 plus 0.9?
It's 1.
It's 1? This signal. So VCM is given. So what's the amplitude? Is it 1.9? 0.9, right? I was just tricking you. It's just 0.9. It's just oscillating around the 1 volt point, but the AC amplitude is 0.9. So then this would be 0.9, and this would give you 90 microvolts. So pretty insignificant, right? So that means the instrumentation amplifier is really good at rejecting common mode signals. And one way you can kind of see that is from the formula we derived. So at the output of the two, so from this formula, what we can see is that maybe if we look at a normal, so if we just look at the instrumentation amplifier by itself, the differential amplifier. So if I was sending in a signal V1 and V2, ideally we set it such that the common mode rejection ratio is 0. But it's highly dependent on the resistor values in that case. Again, just if we're just using this circuit alone, no pre-buffer stages. The common mode signal and the rejection ratio is highly dependent on those resistor values, which vary quite a lot in fabrication. What's the difference when I have an instrumentation amplifier? Why isn't this as much of a problem?
Because you amplify the signal with two buffers,
Yep.
which have much higher UCM or R.
Yep. So essentially, if we were just doing the differential amplifier, the gain of 100 would have to be here. It'd have to be sitting here. We have to get the gain from somewhere. So we'd shift the gain to here. So if there's any shift in the gain, so if there's any shift in these resistors, all of a sudden there's a common mode gain, which is, then that common mode signal is then multiplied by a factor of 100 through the gain, right? Whereas in this system, what's the difference? So you mentioned 1 point, and you said, what did you say? I forgot, sorry. The buffer, you said the buffer?
I said you have a buffer, like the difference between the previous part and like this overall circuit is if you have a buffer, and buffer kind of helps us with this common rejection because we're not reliant on all those being the same, all of these being exactly the same.
Yeah, essentially, exactly. So essentially, we're just less dependent on these resistors now, on these resistor values, right? So we have these pre-buffer stages, which give us the gain and also buffer the signal now. Okay. You can also look from the formula, like the Vout1. I mean, I don't want to overcomplicate it. I think does that make sense? Is that okay? Cool. So then part D is long, unfortunately. We'll get to part D. So, okay. So this is another question where you'd read it and you can probably figure out it's going to be a long question. So in the following, it is assumed that the common mode signal is 1 volt and that the sensed current, so that what the current was sensing, is 0.1 some signal. It is further assumed that the noise in the system is white, that it is dominated by the instrumentation amplifier voltage noise, and that it is band limited by the amplifier. Find the expected signal to noise ratio at the amplifier output. And gives a hint. First find the total RMS noise at the output. Which, yeah, not much of a hint, because I think everyone knows that's what you have to do. But anyway, so I think with these big questions, it's really important to have structure. It can be very easy to get overwhelmed with these big questions. So the first thing I'm going to do is outline what I need to find, then I'm going to go find it, not the other way around, right? Even if I know in my head that it's what I have to find, if you write it down, it just sort of grounds you in the question, right? So part D. So we were told to find the signal to noise ratio, which is the signal over the noise. And these are both at the output. And also to note that both of them, so the noise, when you calculate it, it's going to be an RMS. So you're going to have to calculate the signal and convert it to RMS. Right? So there are two things we need to find. So we'll start with the noise. You could start with either one, but it recommends we'll start with the noise, so we'll start with the noise. Okay. So the first thing to remember with noise is we have, so if we have some, what does it look like? If we have some Vn and some resistor, so you can imagine this is noise coming from the resistor, and then you have some sort of low-pass filter system. This voltage here is so Vn0 we'll call it, and then the resulting, so I'll skip the derivations, but the resulting signal is Vn0 squared is equal to Vn squared multiplied by the 3 dB frequency multiplied by pi on 2. So this is something which you have your notes, you can just look at it, right? Like you have your notes. But it mentions something which is really important, and it mentions that the noise is white. So white noise is what's special about white noise?
Constant magnitude.
Yeah, exactly. So the magnitude of the noise is constant across all frequencies. This formula is derived assuming that the noise is constant along the frequency of which you're integrating the spectral density noise. So then in that case, this formula applies. And just for reference, this is the bandwidth of the noise.
What is that?
Which one, sorry? Yeah, sorry. My writing's not great. It's F3dB. So that's, yeah. But we have an amplifier. Can this model be applied to the amplifier? So you can imagine this is the output of my amplifier, and this is the input of the amplifier, that differential signal. Can this be applied? Yeah. Question. What internally to an op-amp causes the... okay, so someone's asking about common mode rejection ratio. I'll come back to that after I finish this question. But what's missing? There's something that's missing. Gain, right? The amplifier has gain. So what you can do here is you can just modify this by gain squared. And the reason it's squared is because if you have some sort of output equals the gain times the input, we're obviously looking at the power spectral density, so everything is squared. So this is V out squared equals G squared V in squared. So that's why everything is squared. So now this can be applied. And this is legit how I'd approach the question, right? Now it's very clear what I need to find. What I need to find is Vn squared. The bandwidth is easy to find, and I think we know what pi on 2 is. We also know what the gain is. So all I need to find is Vn squared, which is the noise at the input of the amplifier. So let's just see if I can get that easily from the data sheet. Maybe I can cheat this question. So if I look at, so there's a section which says noise voltage. And we're given two voltages. We're given the input stage voltage noise, and oh no, we're given the output stage voltage noise. So that means we have to do a bit of work, right? So they haven't just given us one noise. So you remember we had the two stages. So the first stage being the buffer. That's this one, ENI. Then at the input of the differential amplifier, we have this noise here, EN0. So what I'm going to have to do is I'm going to have to refer all the noise back to the input. So what does the noise look like from the perspective of the input? Okay. So and to make it clear, I will just modify this diagram. So where this noise is sitting, so you have, oh, this is messy. Okay. Is it okay if I rub some stuff out? Okay. So what we have is noise sitting here. So ENI. This is the easy noise, right? Because it's already at the input. So there's nothing to worry about. Oh, it's cutting off a little. Okay, but anyway, it says ENI. The next noise is sitting at the second stage, so it sits here, somewhere there. I think they called it EN0, which is a bit of an unfortunate name, but EN0. Okay. Now, it doesn't actually matter which pin this is on. It can be on either pin. You can prove that to yourself mathematically, but it doesn't matter. Okay.
So why are the transmitted noise in both the pins?
Because that's how it's given to us, unfortunately. So what they're saying on the data sheet is that the noise from the first stage is that, the noise from the second stage is that. So they've given to us separately rather than like a combined quantity.
You want it totally multiplied by 2 in that case?
Multiplied by 2?
Yeah.
Not quite, because the EN0, we have to refer back to the input. We have to see what does this noise look like from the perspective of the input. Does that make sense? You had a question up there?
No,
Oh, same question? Okay. All right, so, yeah, we have a bit of work to do, but not too much. So, okay, so Vn, so we're interested in this one. So this is input noise. Input referred noise. Now, if I look at this noise, so if I go back and I look at this noise, how did it get there? Maybe, yeah, exactly. So one way, so you're right. So one of the ways of looking at it is we can just say, okay, it was the output of the first stage. And what is the gain of the first stage? 100. So can I refer it back to the input? Yeah, I can. So what I can do, yeah, so I can, where's the question? So I can say, okay, the total noise, so Vn squared, is going to be En, I think they called it I or something, Ni squared plus En0 squared on G squared. So again, this comes from this sort of logic. So now I'm concerned with the input, so you just divide G squared on both sides. Okay? Now, from the data sheet, ENI and EN0, I'll just give them to you. They were exactly where I said they were on the data sheet. So ENI equals, and again, for both these cases, I'm taking the worst case, yes?
Question. You are integrating both of the noises, right? One of them comes from the second stage, another one comes from the first stage. You're integrating both noises, and you're going to use the bandwidth for what?
Because it says it's bandwidth of the instrumentation amplifier.
Do we have, because like the first, second stage, you're going to have different bandwidths.
Yeah, I agree.
The first stage, you're going to have much smaller bandwidth than the second one.
Yeah, but I think the question gives a hint on this. I think it says, so it is, okay, it only says that it's dominated by, and that it is band limited, but yeah, okay. In this case, you're right, I do agree. The bandwidths are different. I think we just take whatever the data sheet can give us, right? Because the data sheet is only going to give us the bandwidth of the entire circuit, right? So in that case, you just use whatever's given on the data sheet. Although you make a good point. You had a question on that? Same question, yeah. So was that question clear for everyone? So I think it's a good point that obviously the bandwidth is different for both amplifiers, but all the data sheet gives us is the total bandwidth. So that's just what we're going to use as the bandwidth. Okay. So what it gives us is per square root of hertz squared. Again, this was the same spot I showed it to you, and these are worst case 159 volt hertz squared. And so, yep. And so then when you add these two, did I write it down? Yes, you get 20 per square root of hertz squared. Okay, and that was using a gain of 100. And then I have everything to calculate this, right? I've calculated the input referred noise, the bandwidth you can get from the what's it called? From the circuit as well. Yep. So the bandwidth of the circuit is 60 kilohertz. So again, this is all from the data sheet. Okay, so this is given as 60 kilohertz at G equals 100. Okay, and then when you calculate what Vn0 is squared, you get 615 microvolts squared. Is that okay so far? Any questions? Yes.
I always get confused with like whether to square the value or not when you're talking about. So if it's given 20 nanovolts per square root of hertz squared, is that for ENI squared or just ENI?
I see. So So okay, I think. So you mean, are you talking about the value or the equation?
Like the value, what value we studied, like Vn squared.
So what's given on the data sheet is, actually I think that's a good point. I think I've made a typo. I think they're squared values. So what's given on the data sheet is the non-squared value. What I've written is the squared value, and then I think what I've written there is just a simplified version. So I would have squared them, then added them, then just I took the square root essentially to go back. It's a really weird way of me just trying to make it look simple, but I've overcomplicated it. So yeah, so I would have squared everything in my calculator, and then I just took the square root, so I could write it as a nice square at the end.
So you didn't add it up just on the board?
What is it?
You didn't add EN on the board?
I added that. Sorry, that's because the total result is this, I think. Yep. Yeah, I gotta be honest, I can't remember how I calculated this. I like it, yeah.
Could it be that your N0 is just insignificant when you divide by
Yeah, probably. I think N0 is just insignificant when you divide it by 100. Yeah, okay, that's a good point, right? G is just insignificant. Sorry, when you, EN0 is large, but then you divide it by 100 squared. So it's gonna be a really small number, okay? Now, the next part is to find what the signal. So we found V noise, now we need to find V signal. And what we're told in the question is we're given the current, we're given the sensing current. So we're given the current, we're given this current. Now, the way this works is we have, so I'll just redraw it, we have IS, and we have two resistors here. So this is the RS, and ground. So I'm just redrawing what was given on the circuit. Okay. And then that is V1, and that is V2. Now, we just need to find what V1 and V2 are, because these are the inputs to the instrumentation amplifier. And the way this works is we can see that the current is taking this sort of merry-go-round. And so the voltage drop across this resistor is going to be, so what would the voltage drop across that resistor be? So it'll be minus, negative, right? Because we have a, it's because it's based on the polarity of the resistor. So V1 is going to be negative. So this one is going to be minus IS, RS. And then this one is going to be IS, RS. And the combined sort of difference between them is 2IS, RS. Okay. So now we have an input signal. That's essentially what the circuit is doing. It's sensing a current, and that is getting converted into voltages, which are then going into the instrumentation amplifier to be converted to a signal.
Didn't they say that VCM was 1 volt?
Somewhere. Oh, that's essentially just to say, what is this? It is assume that VCM, you mean this part?
Yeah, so did you like ground it?
That's a good point. But I think it's because, I think the reason they do this is because then VCM is common to both signals. And then I think we can just assume that the instrumentation amplifier is really good at rejecting this signal. Yep. So I think that's a good point. That's probably something you'd maybe write down in your working as an assumption. Yeah. Does that make sense? Cool. And then we know what the gain is once we have an input signal to an instrumentation amplifier. So then we can say V out signal is equal to RMS is equal to 2IS RS times G times 1 on root 2, like that. Okay. And then this signal is 0.99 volts. And when you do both of them, you end up with an SNR of, so I'm just going a little quick now. So SNR equals 64 dB. So that's when you do the V out noise, V out signal divided by V out noise, you get 64 dB. Okay. Now, so in terms of the common mode rejection, so what internally to an op-amp causes the common mode rejection ratio to decrease with frequency increase. So what happens as frequency increases in an amplifier is the parasitic capacitances in an amplifier become a problem now, right? So at high frequencies, those parasitic capacitances look low impedance. They look very attractive. So you imagine if you have something that looks like this, and you have parasitic capacitance that sits here. This parasitic capacitance isn't a problem at low frequencies, but at high frequencies it becomes a problem. Because, and this is very similar to power supply rejection ratio, but essentially what's happening is that the amplifier is not behaving like it should be anymore. Because the input signal, so the input signal is now just finding an alternative path around the transistor, right? And this is happening all across in the inside of that amplifier, right? So the amplifiers are not behaving like they should be anymore at high frequencies, okay? Hopefully that answers your question. Now, next question. So this is a design question. So the ideal value for VSG is half the supply voltage. However, the input offset current can result in a substantial output referred offset, which can be compensated for by making VSG adjustable a few hundred millivolts around the ideal value. So essentially that's this voltage signal. And what it's saying is that there is some noise here. There is some input referred noise, there's some input referred noise here, and that is affecting the reference voltage, right? And so we just need to make VSG adjustable. So how could I make VSG without adjusting? What's a simple way? So party. What's that? Any ideas? Potentiometer, yep. So potentiometer is a good idea. Do I just use a potentiometer? You could. But we want to make it biased around a very particular point. So would it work? You'd have to find a very specific potentiometer, wouldn't you? Yes. Yeah. Yeah. So what you'd need, how I'd approach this question is I'd break it up into two parts. The first part just says generate VSG. Then the second part says make it vary. To generate a reference voltage, the easiest thing is just to use a voltage divider. Not a great reference, but like this. So the easiest thing is to just generate, to put a voltage divider, so you do voltage divide down, and here is your reference voltage. But now we want to make this adjustable, and what we know is we can just use a trim pod. Because at the outskirts, because what's here, we can control what's here. So I can just put in a trim pod there when I control the VSG. So I can put in a trim pod. And the way, I think the trim pod can be a little confusing in some senses. So maybe I'll draw what the actual trim pod looks like. So this trim pod, what it actually looks like, so if this is A, B, C, so this is generally how it's plugged into a resistor diagram. What this actually is two resistors. And then that's the point C. So this would be B, so this would be R, A, B. This would be R, what have I done? Yeah, it would be at the bottom. B, and so this one would be R, B, C. So what a potentiometer actually is the sum of two resistance. Is this right? Yeah, it would be. There we go. It would be RAC. Thank you. So two resistors. Now, what's important is that the sum of these two resistors always equals the same value, no matter what. So let's say this is 200 ohms. RAC plus RBC is always going to be 200 ohms. All that we're doing when you're turning a potentiometer is you're essentially varying. So if I'm turning it, I'm reducing the value of RAC, but at the same time, you're increasing the value of RBC. Right? So what you essentially have is a voltage divider built into your potentiometer. Right? Do we see that, sort of? So it's essentially a voltage divider. But the sum of these, so RAC plus RBC is always the same value. Now, just in the interest of time, I'm just going to skip finding these values. For that, you can have a look at the solutions. But essentially, the idea is you can just vary the resistance. So you set the center point to be VCC, and then you can vary this trim pod such that you vary your voltage. Okay. Before this goes into the, before we actually send this in a reference, we should probably buffer it. So we buffer it. I'll just like this. So it's always a good idea to buffer something to isolate it from the system. Another thing that's always good to include is a capacitor, like this. And that's just to reduce any ripple voltage, because we'd like a constant VSG. Is that okay so far? Good, okay. So this question, I think, was the longest question for sure. It's a bit of a workout, but hopefully that makes sense. For more details, obviously, there are other solutions, but I think we'll leave it there. Would you guys like a break? Okay, I think we'll take a 2-3 minute break. So, oh, I mentioned it was going to go over time. The next two questions won't take as long. This one was just a long question. Okay. Yeah, so stretch your legs. It's okay, 41%. Time-wise, bit of a struggle, but I think it should be okay. I just have to. I think the next question will be quick. Yeah, I think that's just, so in this system that happens, but generally, in some cases where that doesn't apply. That doesn't accidentally happen. I think especially if the bandwidths are different. So it's just, in this case, it happens. I know what you mean. It just pops out like that. No, the bandwidth is a consideration at the end. When you're doing the calculation, you're summing up all the noises. Yeah, it's really something you look at the end. Okay. All right. I think we'll start with the next question. Sorry for a short break. These ones won't take very long. The first question was just super long. So Figure 2a shows a CMOS digital system operating at a supply voltage power supply. The system communicates to another CMOS digital system via a level shifter, U1, and a transmission line. S2 operates at a supply voltage. Okay, we'll just skip all that because all it's saying is that you have system 1 communicating with a NAND gate, which goes along a transmission line to S2. Nothing else, right? And you're given some parameters here. And the first question is to find the noise margin at U1 and explain what to do with its unconnected input. Because what we can see at U1 is the input is disconnected, which is not so good. So I think I'll answer the second part of that question first. So question 2. So what we have is we have a NAND gate with the input. So this input is connected to some Y, but the second input is disconnected. How should I connect it? Yep.
There's two ways. You can either connect it to Y or to power supply.
Yep.
Power supply doesn't matter because you don't lower the output of the previous chip.
Yep. Correct. So there's two options. So the first option, like you did in the lab, is we just tie them together. The reason that works is because in your truth table, or the reason why it's probably the most appropriate way, is the truth table looks like this. Sorry? 2017. Now, we're transmitting data, and we'd like to know when the data flips. So in this case, when we tie the inputs together, we can see that it's either 1 or 0. We'd like probably not to be the middle, because then we don't know which data flipped. Okay. The other option, so or you take your NAND gate. That is a horrible NAND gate. You take your NAND gate, and so this is Y, and you connect up the other input to the power supply, so it's held at a constant value, right? Similar logic would hold for the truth table. Is that okay so far?
Could you also put ground, or is that
No, that wouldn't work. Ground wouldn't work. So Sorry?
Because like it wouldn't fit any.
Yeah, so if we hold, yeah, so it's just based on the truth table. Cool. So then it asks us to calculate the noise margin, so between S1 and the NAND gate. This is the same question. Now, the noise margin is only a useful metric between successive logic gates. It's essentially how high can the noise margin, the noise at the input be before the output stops recognizing it as what it should be, right? So as an example, if this only recognized high voltages as 4 volts, so this NAND gate only recognizes inputs as high if they're higher than 4 volts. If this was 4.2 volts, if the output was 4.2 volts, will it recognize it as high?
Yeah.
What if noise drops it to 3 volts? No. That's all the noise margins are. Okay. So again, we're given another, so for this one, we're given another data sheet. So because we need to find, for the noise margin, we need what the V input high, V output high, all those values. And those you can find here. And you just look for the power supply voltage you're using, and you look for the worst case. That's it, right? There's nothing else to this data sheet, okay? And in that case, you get, how was it working? So you get that the noise margin high is equal to V output high minus V input high, which is 0.13 volts. And you get the noise margin low is V input low minus V output low, which is equal to 0.45 volts. Okay, and that's it. That's the question. Any questions? All good? Okay, next question. Okay, so the U1 output resistance is denoted by RU1. When the U1 output changes, a voltage step travels down the transmission line, is reflected at S2, travels back, and is finally absorbed by a series resistance. During this time, a charge Q0 has been delivered by U1 on the transmission line. It is assumed that the U1 output transmission times are short. So maybe to just explain what that was saying is, so the output is experiencing a low to high transition. When it's experiencing a low to high transition, it's pulled up like that, right? It's pulled to high. But along it being pulled up, it goes to a resistance RU1, right? Because it has to pass through a transistor, and that transistor has some resistance. So that's what that part was saying. And then you have a low to high transition here, like that. And then that is traveling across the transmission line, and it comes back and it's fully absorbed, right? So this signal travels along here, travels back, and is fully absorbed. What does that tell us?
R1 is 0.
Yeah, so just R1?
And we also know about the
Yeah. So maybe let me just draw this out, because we need a drawing anyway to solve the question. So B, O, so B. So what we have essentially is we have RU1, and we have a varying signal, and we have R1, and then we have our transmission line, which is grounded, and then we have our output. Now, the reason we curl the lines like this is just for better transfer of data without too much magnetic interference. So when you coil them like this, you have a magnetic field that coils like that, but then you have one that cancels like that. So adjacent magnetic fields are cancelled with each other. I don't know if that's content, but yeah. It's just to help with magnetic interference. It's also to make sure that both signals pick up similar noise, so that they, when we compare them as a reference, because it's on both of them, there's no problem. Okay. Now, one important thing is we need to figure out what's happening at the end of the transmission line. And the hint I'll give you, or the hint the question gives, is that S2 is CMOS. What does that mean? Yeah.
It has capacitive input impedance.
True?
Small capacitive impedance. So very large capacitor, very small capacitance.
Yeah, very small capacitance.
So basically,
Yeah, basically open, right? So CMOS logic has hardly any current at the input, right? That's just how that's why CMOS logic is so good. Hardly takes any current. So I know that the current going here is roughly 0. So if the current is roughly 0, what does that mean the impedance seen there is? The resistance. Let's say the resistance. It's infinitely large. So if it's infinitely large, that means the wave is going to go there. Is it going to propagate through? It's all going to bounce back, right? So the signal propagates here, bounces there, and fully bounces back and gets absorbed. If it's absorbed, so it goes this way and comes back. Now, because it's absorbed, that means what? So this is Z0. So if it's fully absorbed, and there's no reflections that happen here, what does it mean about what the signal sees as it's coming back? It sees the same impedance, because we don't know what R1 is. That's what we're trying to figure out. But it gives us a clue that the signal doesn't actually reflect back. That means as the signal is traveling, it doesn't see a mismatched impedance. If it saw a mismatched impedance, some of it would come back. But because it sees the same impedance, it just travels as if nothing changed. It travels through the line. So then we can say, therefore, RU1 plus R1 equals Z0. And we are given, what are we given? Something. I don't know what we're given. Let's have a look. Oh, it doesn't matter, right? It doesn't matter. We just need to know what the total resistance is. We're not looking at individual resistances. So, because the question is asking, so, wrong question. So, during this transition, obviously charge is dumped onto the transmission line. It's asking, what is this charge? So, the formula for charge is, what's the formula for charge? IC dt. But if the charge is constant, then this can just be IC times t. So it's the amount of charge accumulated over a period of time. And the reason we needed to calculate the impedance is because we needed what this current was. That current there, that current I. And that current I is just going to be, what's the current going to be?
It's just the voltage divided by in brackets RV1 plus R1 plus Z0.
Good, good. So the current going in is just going to be the voltage. Let's figure out where to write this. Did I write this down as a number? So it's going to be the power supply voltage, because that's what's being put up to, over this impedance and this impedance. Because as the current is traveling, it sees both of these impedances, which we said were the same anyway. So I'm just going to say it's 2 times Z0. And so then this is 16.5 milliamps. And the propagation time t, so how long this charge was running, so how long is the propagation time? So if it went there, so the distance, I should write the distance from here to here is tt. And it traveled back, it went forward once and back forward. So how long was the time? Twice. So this one you take as, what is it? I think it's 10 nanoseconds or something. Yeah, 10 nanoseconds. And then this will give you 0.33 nanocoulombs. And that's the question done. Any questions? Cool. No. Okay, so another long one. I'm probably not going to read it. I'll just tell you what the question is saying. Okay, so it says so there's a certain amount of charge. Both ends of the transmission line use ground planes. Now, the usefulness of ground planes is that at anywhere you need ground, you just drill down to it. Rather than having a long trace to get to ground, you just drill straight down to it and you have ground. So that reduces the amount of impedance along the ground lines. So it's just saying you can ignore the ground impedance. However, the supply voltage series impedances not shown are large. C1 is 5 nanofarads. U1 is the supply decoupling capacitor, which powers U1 during a transition event on the transmission line. C1 is being recharged to VCCU between events. C1 is the voltage. Yeah, it's a lot of words. So essentially it just wants us to sketch the voltages during the transition. Now, maybe if I draw what it's talking about, it'll be easier. So in the transition, so the NAND gate is sitting here, and this is ground. Now, when a low to high transition, we know it's going to be pulled high. And it told us that the impedances in the power line can't be ignored. And hopefully from the lab, we know that this impedance is like this. So it's an inductive impedance along the coil. And then essentially I can model everything to the right of the NAND gate as just a capacitive loading effect on the NAND gate, okay? Just for now. So C load. So, okay, so maybe I'll just talk about how I'm approaching this question. So it's asking me to sketch VC1 during both high to low and low to high transitions. C1 is that decoupling capacitor there, right? But before I actually get into the question, what I think about is what is C1 actually charging and what is C1 doing? What's the point of C1, just looking at it? Yeah. So it's a decoupling capacitor, right? And so that's essentially what I'm going through. Before I actually sketch, we need to figure out what C1 is doing. But not just what it's doing, but how much voltage it's providing to the load capacitance it's seeing. Okay? So during a transition, a lot of current is pulled to charge that capacitor. This results in a large voltage drop across the inductor. And because of the large voltage drop across the inductor and the capacitance, that means you're going to have dips in your power supply. So if this is, so it's going to be like, so at each transition, because of the voltage across the inductor, right, that's going to cause a dip and spike VCC. Hopefully you would have seen this in the lab. And the way we mitigate this is we put a capacitance like this. So this would be a decoupling capacitor. Now, VCC still charges this capacitor, but what you'll notice is that it charges the capacitor outside of the transition, right? We don't want it to be charging, we don't want these dips during a transition, because during a transition, this dip could go below the NAND gate's allowable range. So it charges this capacitor when no transition is occurring, because you see that loop? It has nothing to do with the NAND gate. But then when a transition does occur, instead of taking the current from here, it takes it from here, right? It takes it from the coupling capacitor. So we've essentially bypassed VCC during any transition. Is that okay so far? Good. Yes, cool. So now we need to figure out, because again, it's asking us to sketch what is happening. So this is C1. It's asking us to sketch what is happening at VC1. So VC1 charges up to what value? Again, outside of any transition, what is it charging up to? VCC, right? It doesn't need to go through the NAND gate, so it's going to charge up to VCC. And then we need to figure out what is it dropping down to, right? Because it has to supply charge to CL, right? So the voltage across it is going to drop because it's losing charge, because it's giving some of the charge back to CL. But then once it's given that charge back to CL, does it charge back up or does it stay where it is? Charges back up, right? That's all we have to do for this question, right? That's all, it's just a lot of words. So, and hopefully I've broken it down in an easier way to understand. So because it's just saying sketch what's happening at that capacitor C1 during both high to low and low to high transitions and mark relevant voltages and times. Okay. Okay, it does get a little tricky, but let's keep it simple. So we know there's a formula that's voltage. What's the formula for voltage across a capacitor? Yeah. So it's Q over C. And so the amount of voltage that it's going to change by, did I write the values down? Yes, I did. So we're given Q naught, so we're given Q naught. So Q naught, remember, was what we calculated in the previous question. That was the amount of charge required during a transition. They've just given us a value, so use the given value. Do not use your previous value. Okay. So Q naught on which capacitor? C1 or CL? C1, the coupling capacitor, and so but now this is the tricky part. Now we have to draw it across time. And we know this is a transmission line. So we know there's going to be reflections, propagation delays, and a few things to keep in mind. So what I'm going to do is I'm going to draw two graphs. I'm going to draw what is happening here. So I'm going to draw V, call it U1. So I'm going to draw the output at the voltage of the transmission line and compare it with the voltage of C1. Okay. And again, the reason I'm doing this is because what's happening at C1 is affected by VU1. And VU1 doesn't change instantaneously. It's a transmission line. So voltage will go back, and then we have to wait for that voltage to come back before we can draw the rest of the graph. All right, so I'll draw T, V, U1. So now, during a low to high transition, is that voltage going to change instantly? So if I apply, if there's a NAND gate and this ups to VCC, and I'm probing this voltage as VU1, is VU1 going to jump up to VCC?
Yes. It's going to jump to half VCC.
Why half VCC?
And what's voltage division?
Yeah, so VU1 initially is not VCC, right? There's a voltage division between those two resistors and the transmission line. So that's going to be VCC on 2 initially. Where'd it go? So it's going to jump up like that to VCC on 2. Then, as we know, this goes down the transmission line, and what does it do? Comes back, right? And so if VCC on 2 is going down the transmission line, we wait 20 nanoseconds, and VCC on 2 comes back as well. So what do we end up with at the end? VCC. Is this okay so far? This one can be a little confusing. So we start at VCC on 2, but then don't forget that it's split between two waves. So we have VCC on 2, but VCC on 2 is also sent down the transmission line. So we wait for it to come back, and it adds on to what we already had. Is that okay? Yeah.
Why does VU1 start with VCC over 2 and not at VCC?
Good question. So, sorry, just to reiterate for everyone online, the question was, why do we start with VCC on 2? What was the last part of the question?
Why does VU1 start at VCC over 2?
So it starts off at VCC on 2 because, so maybe we'll look at this circuit. Somewhere. Where did I draw it? Okay, here. Just because of simple voltage division, right? This is in the absence of any propagation. We know it's going to be VCC on 2 because there's a voltage division between those two resistances, which is Z0. And then, because we said that this one and this one were perfectly matched, so it's going to be like a voltage division by 2. That's why we start at VCC on 2. But VCC on 2 is also sent down the transmission line and comes back. Okay? And that's why after 20 nanoseconds, where is it? So after 20 nanoseconds, nothing happens. After 20 nanoseconds, it jumps up to VCC. Then let's imagine, whatever, I stay high for a little bit, and then it also asks for a low to high transition. A low to high transition is just going to do the exact same thing, right? There's no reason it shouldn't just obey the same sort of principle. So it's going to drop down, so this is high, low to high. But now comes a bit of a tricky part. What is happening to the charge? What is happening to the capacitor during that low to high transition? So let's maybe just underneath this, draw the voltage across the capacitor. So if I take this point, this point, this point. So what does it start at? What voltage does it start at? The capacitor. So this is voltage across that decoupling capacitor, VC1. It's charged up to VCC. So VCC. And then a transition happens and it drops by, what did we say? 100 millivolts? Because this is the charge required. So it gives charge to the load capacitance. and it drops to VCC minus 100 millivolts, like that. And then nothing is happening, so no transition. So what happens now? Charges back up to VCC. But now what happens during the low to high transition? Pulls? Not saying you're wrong, but can you elaborate? So someone said pulls. So if we look back, I haven't drawn it. Okay, so we'll look back at this circuit. So now we're going from a high to low. So what's happening during a high to low transition that's different to a low to high? What's the difference? I'll come back to you after. Pushing it to a higher charge? So you're saying, I'm not saying it's wrong, but you're saying C1 would increase? Increase? Okay, so we experience a low to high transition. That means, does that mean we're pulling high anymore? We go from high, how do we pull low? That means inside the NAND gate has to be pulled to what? For a low input. Not a trick question, I promise. So it was pulled to high for VCC, but then a high to low transition happens. How does it become low? Ground. That's it, right? It's so we no longer have this anymore, and we are now pulled to ground. All right. Now what?
The resistance in the NAND gate might not be the same as RU1 anymore.
Yeah.
Yes. So it might no longer affect completely, absorb completely.
Yeah, that's true. What about VC1? Because we're interested. So you're not wrong. The pull up and pull down resistances will be different. But what happens to the voltage across VC1? Because that's what we're interested in, really. What is happening? Nothing. Does it need to charge up the capacitance anymore? What's happening to the charge across CL when we pull low?
It just shorts.
Just goes to ground. Right? Because when we're pulling to ground, we're providing the capacitor a path to discharge. So no longer do we actually need VCC during this high to low transition. VCC is only affected in that low to high transition. Right? So if I go back to my diagram, what's going to happen during this time? Nothing. Right? Nothing. It's just going to stay constant. And that would be the end of that question. Was there any questions on this? These are quite tricky questions, which is why I wanted to cover this. There are other similar transmission line questions, but the approach is really the same. Okay. Now, next question is very short, thankfully. Wrong question. So, explain a likely cause for having large supply voltage series impedances. So we can just talk about this one. So why do we have such large inductances on these wires? What's the likely cause? Yeah. So just the longer the wire, the more inductance we'll have along the wire. So usually you have PCB tracks. If you make the PCB track too long, you get these large impedances along the wire. Did I note anything else down? I think that's pretty much it. Yeah, that's pretty much it. Yeah. So it's a nice break after part C. Was there any questions? Cool. Now, the next one is a design question. So this one's interesting. So it is now desired to have an LED light up whenever there is activity on the transmission line, i.e. when the U1 output toggles. Design a circuit that implements this LED activity light function. So maybe just to make it a little clearer, I'll outline what needs to be done. So this is part E. So we have our NAND gate that looks like this. And you have some transmission line, like that, some transmission line. And when this output toggles, we'd like to be able to detect it with an LED. How might we achieve this?
Question.
Mm-hmm.
Do you want it to light up just when there's a changing signal, or for all the time when there was a signal in the transmission line?
I don't think it specifies it, so it's desired. Yeah, so ideally, I mean, it should be a little more clearer, but ideally, I think it's up for interpretation, to be honest. It doesn't say I don't think you could be penalized for either, because it doesn't say in the question. As long as you carefully write out what you think. One thing I'll note is even if you can't find a design solution, if you can kind of give a rough outline of what you think should happen, you'll still get marks, right? You don't have to know how to, because figuring out how to implement something can be difficult. But if you know what has to be done, but you just can't figure out how to implement it, still write it. You still get plenty of marks for that.
And because the simplest way to do this question would be like that you just rely on the fact that the finish line doubles the equal, but you light up for 20 nanoseconds. It's obviously invisible.
Yeah. So I think you have to put in an element of like practicality into it. Yeah, a 20 nanosecond LED maybe isn't long enough. What could be a solution? Just anything. Yeah.
How could we use that comparator? Because you know the voltage will change when there's a toggle, right? So if we compare that to a reference voltage, we could maybe LED light up it's the same.
Yeah, that's a good solution. So we use a comparator. So we compare. So what type of comparator? Like an op-amp? So you mean like you have some reference voltage and your signal comes in like that? Like that? Yeah. Would this toggle though? That's my question. Would this toggle? So this is a good solution, but would it toggle?
No, what do you mean by toggle?
So we want it to toggle. So I'm not saying you're wrong, I want you to elaborate. What is it? Email? Yes.
Then would it work really well because we just light up for all the time when the finish line has high note or when it has low note? Is it configuration to be when it's low note?
Yeah.
So it would indicate transition, it would just indicate the state.
Yep.
Which would not like.
So the point here, so this would still be a good solution you'd actually get lots of marks for. But the point to make is that we want it to toggle, right? We want it to toggle so it can detect any changes. Yeah, so.
This way we can do just to have just to add I want a stable multivibrator, like a latch of some sort. I want a stable latch.
A latch would work.
Of fixed length to make sure we can see and I can see like the LED blink.
Yeah, so that solution is essentially to put in, so that solution would, so if this was your solution in the exam, you'd probably still get 3 out of 5 for that question. But the problem is it's not, if we go to the question, we want it to detect toggling, right? But what would be the problem? Can you tell me what the problem with this would be? Looking at it. So I'll come back to your solution in a second.
Is it like will LED light remain on even though there's a transition?
Yeah, so the problem is it's going to stay on, right? Even when there's a transition. So the other solution is to use a latch. And what would you use with the latch?
Like some kind of RC tempos, like a simple
Yep.
unstable multivibrator.
Yep. So based on, so this is bouncing off of the same solution you just had, but taking a little further, we could probably use something like a Schmidt trigger with some hysteresis, right? And the reason a Schmidt trigger with hysteresis is good because we can use then an RC time constant network to charge and discharge between these hysteresis levels when a change is happening, right? So to give you an example, so you could have like a Schmidt trigger and an RC time constant like this. Like this. Like that. Now, the way this works, so CR. Now, when there is a change on the transmission line, like this, what happens at the capacitor, at the right side of the capacitor? Yep, so it's going to spike up as well, right? So when there's an increase at the node of the capacitor, so that increase is here, this voltage is also going to immediately increase because voltage across a capacitor can't change instantaneously. So it's just going to match whatever it sees on the left-hand side as well. And then it's going to discharge through the resistor, right? So it's going to pull up to VCC, or VCC on 2, whatever, and then it's going to discharge through that resistor, right? It just spikes up initially because it just matches whatever it sees, right? And then it discharges. But what you can see is that the Schmitt trigger can detect this change. It can detect this change upwards. So if I draw the Schmitt trigger quickly, so it's inverting, so we'd have like this. So this is the input versus output of a Schmitt trigger. Now, if the input swings up to VCC, so I'm going to swing up to VCC like that, and then what happens after this? So I swing up. Sorry? Stays there? So I swing up. Do I stay here? So I'm looking at the right side of the capacitor, because the right side of the capacitor is what's going into the Schmitt trigger. So I swing up, then what? Goes back down, because remember, it's discharges to ground. So then it's going to go to the right or to the left? To the right, and it's going to switch. So you can see how it detects that change, and then it switches back. Okay? So this is what we call like a negative edge detector circuit. Very, very useful for a lot of applications. But there's a problem with this. If you try using this, it's not going to work.
Why is there need to have a resistor to ground?
To provide, well, essentially to provide a discharge path, right? That's pretty much it. Because we want to detect toggling, right? And also it gives us a time constant fix. If you don't put this resistor, it relies on the input resistance of the Schmitt trigger. Probably not great. So it just gives us a fixed time constant. But if I build this, it's not going to work. Can someone tell me why? Maybe that's a hint. What happens on the low to high transition? So maybe if I, so I won't give away the solution, but maybe if I, so it goes from, so now I'm assuming we were at VCC, so the input was high for a long time, and then I dropped to 0. I'll let everyone think for a bit. So think about what happens on the right side of the capacitor. Any ideas?
It would remain the same.
What would remain the same?
So because the voltage, capacitor not be the same.
So this voltage was sitting at 0 volts. So it was sitting at 0 volts on the right-hand side from the last scenario we were just in, because it's already discharged. So it starts at 0, and then drops down to what voltage? Negative VCC, right? It matches what it sees. So it goes from 0 to negative VCC. Why is this bad? Yeah, the Schmitt trigger does not have this range, right? It cannot handle a negative VCC. Generally, it's like ground minus 0.3 volts it can handle, but we're throwing in negative 3.3 volts. This can be really bad for the Schmitt trigger. How could we fix this? Parts of it. So you're not wrong, but technically this is not a problem of like us touching a circuit, but you would have to use something similar though. Something similar, yes.
There's no need because most proper chips already have a die instead of some die in the ground.
Yeah, I know. But let's pretend that's not happening.
Then you just have a die
Yeah.
it's the negative from the ground up to
Yeah.
up to
So one way we could do it is we could clamp this negative VCC, right? So we can, instead of letting it drop down to negative VCC, I can put like a Zener diode, or you can just put a diode here. And so this diode will turn on when this drops to negative VCC, but the voltage it drops to is no longer negative VCC. It drops to whatever this forward voltage is, right? So you can imagine it'll just fix to minus negative 0.6 volts. So instead of dropping down to negative VCC, it'll drop down to the point where the diode turns on. Okay? Oh, sorry. It'll drop down to enough voltage to keep that diode on. Now, as you rightfully mentioned, most of the time this is in the Schmitt trigger, but good point to mention. Yeah. So I would just mention that this diode probably isn't even necessary for probably for a full solution, but yeah.
Does the Zener diode die with time? It's like connected from ground to.
This isn't a Zener diode, it's a regular diode.
Oh, it's a regular.
Cool. That ends that question. Any questions? Cool. And I'll just mention there are plenty of solutions to this. You could use a latch, you could do the comparator sort of topology. But what is always going to be your best friend in these design questions is an RC time constant filter, right? It is always going to be your best friend. Like, most of these solutions have an RC filter in them. I think there was one question, I won't spoil it because you're going to get to the past papers yourself. But yeah, you're going to find that it's a common theme for detection circuits. Okay. So, very last question. Now, the only really long part is the last part of this question. But this question is a really good question because it covers things like LDOs, power amplifiers, and all that. So, the system shown in Figure 3a uses a lithium battery as its power source. So that's this battery here. The battery's discharge profile at different temperatures are shown in Figure 3b. That's this figure. Its capacity and terminal voltage are assumed independent of its load current. The system makes use of a low dropout linear regulator to generate a constant supply voltage. So all that means is, even if this voltage fluctuates, whatever, this one hardly fluctuates. That's all it means. So we just get a nice, clean, symmetric DC. I guess. Yeah, so this is going a little over time, but it will finish before 3. So the system must be functional over the temperature range, minus 10 degrees Celsius to 60 degrees Celsius. Further, the dropout voltage for the LDOs VDO equals 0.2 volts. Now, when you're approaching a system like this with so many different components in it, it's important to isolate what's actually necessary. So I can see that there's transistors at the end, but have they been mentioned in the question? No, I don't see any mention of Q1 and Q2. So for that part, we can just ignore it, right? Most of these questions, you're not going to need the entire circuit. Even when we were analyzing the previous question, sometimes we just needed the transmission line after the NAND gate. We didn't actually care what was before the NAND gate, right? So just isolating can be very useful for these questions. So the system must be functional over a particular temperature range. Further, the dropout voltage for the LDO is 0.2 volts. Find the worst case useful battery capacity QCW. So how I would start this question is I'd write a formula down for QCW. Right? That'll immediately tell me what I need. Right? Rather than trying to figure out why did it give me dropout voltage, I can figure out that later. Just first write down the goal. Okay. So part question 3, part A. Oh yes. Paper, sorry. Yeah. So this is 2020. This is from the 2020 paper. Question 3. So the charge capacity, so the formula for charge isn't going to change. So when we're thinking about battery capacity, it's how much charge can it give over a period of time before it dies out, or before the circuit fails. So this would be the integral of I C dt over some time period. But we're given that the charge is essentially constant. So I can just write this as IC times T life. So how long the battery lasts. Okay. Now I can clearly see what I need. I need the current and I need the lifetime of this battery. The current is actually given. Just close that. The current is given. Is it given? Should be given. Oh no, okay, we need to work out the current as well, I just remembered. Okay, so we need to figure out 2 things. So can we just, looking at this diagram, can we see what IC must be? Yep. So IC is just going to be ICC plus I LDO. Yep. And I'm trying to figure out which one's easiest to go through. Maybe let's start with the lifetime of the battery. Let's do that. Okay, so the battery is connected. And by the way, what I'm about to write isn't really what you need for the question, but I think it's important to go through. So the battery, is a horrible battery, VC is going into an LDO. So when we think about worst case battery capacity, we need to think about when does the circuit actually die out? When does the circuit stop charging? Because we have these discharge profiles. But we need to figure out how long, because on the x-axis is time. So how long is it going to charge for? What is its worst case lifetime? Its worst case lifetime is dependent on the amount of voltage it discharges to, right? So it starts at some voltage and then it discharges to some voltage. The voltage it'll stop discharging at is when the circuit breaks, right? When the circuit stops functioning. So now an LDO looks like this. So V in. I will explain in a second. So that's the output. So essentially we have an output and then we divide it down as a reference voltage and we send it to a comparator, right? And we compare it with some reference voltage, Vref. Now, the usefulness of this is that so this voltage here is some scaled version of V out, right? Depending on how you choose those resistors. Now, if beta V out changes because the output is changing, it changes what is at the output of the op amp, right? And this is extremely common in feedback loops to use a BJT as a sort of resistor. So what happens as the output of the as the output of the op amp grows and it drives more current, what happens to the BJT? Does it start sinking more current or less current? So I'm referring to this current here. So IC. So as the output of the op amp grows into the BJT and it starts sending in more current, does IC grow or decrease? Grows, right? So if there's a problem with V out, right, let's say the load is demanding a lot of current, what will happen is that the op amp will output lots of current into the BJT, which forces it to bring more current because the load is the load is demanding more current. And so to keep V out constant, we have to provide that current to the load. And this BJT is essentially, all it's doing is acting like a variable resistor. We can just approximate it as a variable resistor, like a trim pot. Right? I just drive more current and it changes the resistance of that BJT. The lower that resistance, the more current is pulled. And in any question which recommends using a feedback network, something like this is always used with some sort of BJT in any of the design questions. So another sort of useful tool to have in your tool belt. Okay. Now, one key consideration of what's happening here, let me just delete that, is that we need to keep this BJT on, or a MOSFET. So we need to keep this BJT on. So, and remember, we're calculating the worst case battery capacity. Worst case would be when this LDO stops working. An LDO stops working when we don't provide enough dropout voltage to bias the transistor. So that means our V in, so V in minus V out must be greater than the dropout voltage to keep the BJT on. And I think that was given as 0.2 volts. And V in, don't forget, is our battery voltage. So I can rearrange this and I can say, okay, V in needs to be greater than V dropout plus V out. And sorry, what was VDO? I don't know if I have it. Sorry? 0.2 volts? Good. Okay. And also, we're told, so what is the output of the LDO? Sorry? No, what was that? Sorry, I should clarify. I meant voltage. What is the voltage? What does it say there?
2.5.
Yeah, it's VCC. It's 2.5. We're given that. So it's going to be 2.5. So then this is 2.7 volts. So 2.7 volts. And then we go look at our discharge profile. And we want to look for the worst case discharge profile. So we have a range of temperatures. So we know it's going to discharge to 2.7. So 2.7 is there. Because the circuit's going to stop working at 2.7. So if I look across, that line is there. So which temperature graph would you pick?
-10.
-10, yeah. So we would pick -10. And why would we pick -10?
Because it's the worst case.
Yeah, worst case. It's the shortest that the battery actually lives for, right? So you could pick any point. I think Torsten picks like 775, which is a little inconvenient. So you can just pick like a point here as like 750. It doesn't really matter as long as you're close. Okay? So we can see that the lifetime is 750 hours. Right? So then, so we go back to our equation up here. And did I write these numbers down? Yeah. I think it's supposed to give what the current is in the question. Oh, I'm so blind. It says load 190 microamps. Yeah, that's what I was looking for. So it says load 190 microamps. Okay. So then in that case, this is 190 microamps multiplied by 750 hours, which is approximately 147 milliampere Henry. Okay? And that's done. Any questions? Okay. So really just always, anytime you approach this question, define what you need first. Even if you think you know it in your head, just having it written down makes it so much easier. Okay? Next. Part B. Okay. The system makes use of a power amplifier to drive a load. When the power amplifier is active, the system supply current, just scroll up a bit, is at a maximum ICC ETX equals 20 milliamps. The LDO draws a constant current of 20 microamps at all times, so that's this current here, while its junction to ambient thermal resistance is given as that. Find if the LDO requires a heatsink. Any ideas? As to how to approach.
We can start with doing the equivalent circuit, the thermal one.
Yeah, I think in that case, that I don't think we can because we're only given theta GA. So we're only given the junction to ambient temperature, which is a hint that maybe we don't.
Calculate the others in this case.
Sorry, say it again.
You have to calculate others.
Most of the time, you'd have to be given them. Because we don't have enough information to calculate everything else. Because we don't even know what the heatsink is, right? To calculate those sort of things, then you need to know what the heatsink value is. You need to know if there's a heatsink. The question is asking us to take a step back and say, does it even need a heatsink? So junction to ambient temperature, so the junction it's referring to is essentially the output of the LDO, sitting there. It's saying, does this temperature get so hot to the point where we need a heatsink? How would we know if it gets really hot? So one really quick hint is the units are given as 85 kilowatts. Okay, I said it. 85 kelvins per watt.
In this case, then we calculate power.
We calculate power, right? So because we can see the unit is 85 kelvins per watt. So we need to find the power in the LDO. So if we go back up to this drawing I made, the current it was referring to as the LDO current is this current. So that current is 20 microamps, which is, I mean, non-existent. You can kind of ignore it. I'm just going to include it for the sake of completeness, but you'll see even the final answer, it's almost nothing. And the reason for that is because the op-amp draws no current. Okay. Now, cool. So we're also given that the current, when the power amplifiers are on, jumps up to 20 milliamps. So even now, even still, we still don't need to care about what's happening on the power amplifiers. It tells us what the current is. Okay. So the current, where would that current be in this circuit? That 20 milliamps that's coming out of the LDO. Yeah, at the output, here. That current there. So that current would be 20 milliamps. So can we calculate power from this? So if we know the voltages, we know the currents, surely we can calculate power. Right? So power, so P, what did I name it? Okay, I gave it horrible names. P LDO, which I'm going to define as the power due to this current. So we have to consider currents at each node. So 20 microamps, what would the voltage be at that node? So this voltage was always VCC, because it's a power supply voltage. So then this would be VCC multiplied by ILDO. There's also an output current. What would this output current be? Output power. Say it again. So 20 milliamps times VCC, just VCC? So now I think this is a tricky part. So now we have to think about how is the LDO actually getting rid of voltage or getting rid of current. So the way the LDO works is, say you want to step down from 5 to 4 volts. It has to get rid of that 1 volt somewhere. It gets rid of it via heat through that transistor. Right? That transistor has some resistance. The reason it has a 0.2 voltage drop is because it has some resistance. So the power, as a result of the output voltage and the output current, is being lost where that BJT is as heat. Right? So maybe for a simpler explanation, you can think of it like this. So that 20 milliamps came from the input and went like this. Right? Maybe now it's a little clearer. So because we're assuming that that 20 microamps is really small, so the input current is basically the output current, and it passes through that dropout resistor. And that's how it dissipates heat and drops the voltage down. So, how am I going? So then the output power is going to be V in minus V out times IDO. I think they call it CCTX. And this thing is just V dropout. So then total power is, so when you add these two numbers, you get 12 milliwatts. So you can just sub in all the numbers and you get 12 milliwatts. And then, 12.1 milliwatts because of that 20 microamps, so basically negligible. And then the change in temperature using that theta JA, so this thing was 85 kelvins per watt. So you multiply by power and you get 1.03 kelvins. So would a heat sink be needed? Probably not, right? That's basically nothing. So it doesn't get very hot, so our answer would be no heat sink is necessary. Okay? Next question is short. So in the following, it is assumed that QCW equals 150 milliampere henries. The desired system battery life is T life equals 3 months. To achieve this, the core system of the power amplifier is active only for D equals 0.1% and powered down otherwise. ICC is reduced to a value. Okay, so it's saying that for 0.1% of the time, the power amplifier is active. For 1 minus D time, the power amplifier is not active. So it's not drawing very much current. So then we need to find the maximum allowed system current in the idle state, ICC idle. Again, another way to approach this question is just to define first what we have in the system, right? Because to find so ICC idle is the current in the off state. To find the maximum allowed off current, we have to figure out how much current there was in the on state. Because say we have a battery capacity, so there's only so much current we can output. So we have to see how much was used by the output. So the output, so this is part C. So the output current, sorry, what am I writing? So how did I write it? Okay, I just said IC. So IC, which is the current coming out of the battery, it's always going to be the LDO current plus ICC. I mean, you could probably just ignore it, but the solutions include it, so I'm just going to include it for completeness. So ILDO plus ICC, that's the total current. And we know that this is going to be split between 2 cycles, right? The first cycle being when the power amplifier is on. So that's, what did they call it? ICC TX plus ILDO. Because remember, the LDO is always drawing current no matter what, right? And then plus, what's the next case?
D minus 1.
Yeah. so 1 minus D when it's off. And in this case, it's ICC is much lower, plus IODO. And this current, sorry, I should have written, this is ICC idle. So we have the on and off case. So on and off. And then what we are given, so remember there's a battery, so it is assumed that we have a certain battery capacity, and so that's going to limit how much current we can have, because Q equals ICT, and we're also told its lifetime is 3 months. Okay, so we're told its lifetime and its battery capacity. So from that we can rearrange this and we can say therefore IC equals Q on T. And when you sub in what you're given as Q on T, don't forget to convert T to hours. Because it's given in 3 months. Obviously we don't want 3 months, so you should convert it into hours because the unit of QCW is milliamp hours. Yeah, it's a good question. I think depends what time of the year it is. Yeah, just state whatever your assumption is. Whether you use, if you use like 30, 60, 90 days, that's fine. I think Torsten does 92 days. Don't know why. Yeah, assume we're in February, so 28 days. I think I would personally do 30 days, like times 3. But yeah, just say your assumption. And then this would give you 67.9 microamps. Cool. And then if we look at, okay, here's the equation. Now IODO we know as 20 microamps. ICC TX we were given. ICC idle is what we're trying to find, and we know D is 0.1%. So can I just rearrange this equation to find IC? Yeah, I can. And I just calculated what IC should be. So you rearrange the two equations, and you get hence IC equals IC idle equals 27.9 microamps in the worst case. And that's what we get. Okay. Any questions? Cool. Now, next, so part E isn't. Okay. Okay, we'll start with part D. So the power amplifier is a class A structure with Q2 acting as a constant current source and Q1 acting as a common collector amplifier. So remind me what a class A amplifier was. How was it biased? In the middle. And then we were just swinging it up and down. So if we look at, this one is built with 2 transistors. And this is the reason I picked this question, because I think this can be a little confusing. So this isn't acting in a push-pull configuration. And the question mentions that it's not acting in a push-pull configuration, because we know class A never goes negative, right? The input is always biased so that it stays positive, right? It never drops below 0. So it's not acting in a push-pull configuration. You can also tell because we have 2 NPN transistors. When you have a push-pull configuration, it's NPN, PNP. What that bottom transistor is doing is it's acting as a constant current source. So part D. So you have a transistor like this. So your input is here, VCC, and you have another transistor here, VB. Now, V in can vary, but VB is a constant value. VB essentially just controls the amount of current flowing here. Right? So the way I showed previously to bias the transistor was you change the voltage at the input, and you vary it until you get a current you like. The other alternative is you just force the current to be the value you need for biasing. There are 2 options, right? They've gone with the second option of just forcing the current. Like this entire thing can just be represented with a current source to ground. That's all it is. It's just a current source because VB controls the amount of current, right? You increase VB, you increase the amount of current, and VB is a constant value, so the current is going to stay fixed. And that current is going to stay fixed all throughout. Okay, and that sets us in the middle point, or at least they can derive it that way. So that's what the question is saying when it says it's a class A structure with Q2 acting as a constant current source and Q1 acting as a common collector amplifier. The other difference is we were applying the input. So if we go back, the input, yeah, okay, no, there's no other difference, that's pretty much the same. So for both transistors, it gives us two values for which, so VBE equals 0.6 volts, and VCE greater than 0.2 volts is required. That's just to keep the transistor in the forward active mode. The transistor base voltages may be in the range VI greater than 0, VB less than VCC. The load is RL equals 50 ohms, and C2 is very large. It is assumed that the load voltage VO is a pure sinusoid. Find the maximum power that can be delivered to RL, PL max. Okay, so there's quite a lot in that question. Again, with an overwhelming question like this, I just skip all the detail, and I look at part D, which tells me what to find, and then I work backwards. So we'll come back to all that information, but I just want to look at the question, which is find the maximum power that can be delivered to RL. What we need to find, so I'll just delete all this. So then we have a resistor here. And we need to find the maximum power. So we need to know what the voltage here is. So V out. Now, the maximum power is going to be dependent on how much this output is allowed to swing, right? Because the output power is going to be the maximum voltage, V out max. So that's the voltage it's allowed to swing in the positive direction before it turns one of the transistors off. And also V out max, V out min. So this is the lowest it can swing to before one of the transistors turns off. Okay? So, because when we're thinking about power amplifiers, this is large signal analysis. So the voltage swings are large. So we need to think about what happens as it swings up and as it swings down across this resistor. Okay? And also because it's an AC wave, so we look at the maximum and the minimum point for power. So V out max squared times 1 on RL. Now, why this was useful for defining what to do is now it's pretty clear what needs to be found. I know what RL is. What is unknown here? V out max and V out min. Right? So now all of a sudden everything they were giving me in the question becomes a lot clearer. They were giving us conditions for when the transistor stays on. Okay? So V out max, so I'll give you a quick way, or sort of a fast way of approaching these problems. Okay? So minus VBE, and then that there is VCE. That's what we're given. Now, to determine if V out will affect the transistor, you have to look at, will affect either of these voltages. You have to look at whether or not it is related to those voltages. Is it related to both of those voltages? Like, is VCE affected by V out? So VCE is the collector, which is at VCC. Where's the emitter at? V out. And same with VBE. It's dependent on the emitter. If we look at this bottom transistor, this is VBE for the bottom transistor, and this is VCE of that transistor. Now, if we look at the bottom transistor, is VCE affected by V out? Yeah. Is VBE? No. So we know which one to ignore. We don't have to worry about VBE. We have to look at VCE, VBE, and VCE. You have to look at all three of them, right? So the first thing I'll look at is that VCE, so first thing, is VCE has to be greater than VCC minus V out. Right? So that's just because the voltage drop that has to be maintained. Sorry. Let me just write it like this. This is equal to that, which has to be greater than 0.2 volts. So then, therefore, I can just rearrange this and I can say, therefore, V out is greater than or less than or equal to VCC minus 0.2 volts. That's one condition. Okay. So if the voltage swings above this, the transistors will turn off and it won't act like a power amplifier anymore. The next condition is VBE. So VBE, how would I do VBE? So what's at the base? Yeah, yeah, so at the base, that's correct. So at the base is Vin, at the emitter is Vout. So you would say Vin minus Vout must be greater than or equal to 0.7 volts. And 0.7 volts is essentially VBE. So then that means, therefore, Vout must be less than or equal to Vin minus 0.7 volts. Yeah, sorry, you're spot on. The question says 0.6. My apologies. Okay, so 0.6 volts. So now we have two conditions, right? Which one do we use? So VCC, sorry? The worst case. But what is Vin in the worst case? Because in this one we have VCC minus 0.2, it's obvious. But what is Vin in the worst case? 0? If it's 0, then we have Vout must be less than minus 0.6 volts, which is... Oh wait, I've written this wrong, my apologies. This is Vin greater. Like that. Okay, so this is not a... They're not conflicting, my apologies. Because then you... No, they're... Oh my god. Sorry, it's been a long 3 hours. Okay, so we have two opposing conditions. So you mentioned, so maybe let's calculate what this top one is. So VCC, someone remind me what VCC was? 2.5. So then this will be 2.3 volts. And then Vin is, so Vout needs to be less, so worst case, would it be 0? So if the input is 0. I'm not saying it's wrong, I'm just asking. Because we're looking for the worst case scenario, which limits Vout a lot. 0? Which one? Negative? We have to infer what Vn is, which is the problem. This one's a little difficult. We have to infer what Vn is. What do we think Vn is? 0.6? So 0.6 is VBE. If Vn is 0.6, then... Yeah, but is that the worst case? Tricky question. What we're trying to figure out, so yes, we're trying to figure out, so we're assuming everything is remaining in forward active mode, and that's what these conditions are imposing. If this condition is satisfied, then yes. But the tricky thing here is we can't have too many things varying. We can't have Vin and Vout varying, right? So we're trying to figure out, at the worst case of Vin, what does Vout have to be? If it was the other way around, you're right. So if we control what Vout is, we say Vout has to be this, then we work backwards and say, okay, Vn can be this. But for Vout, we have to look at the worst case, and we have to say we always have to keep it less than this. From the other transistor? Yes. So we're going to use that to determine the lower bound, but it's not related to Vn.
Also the requirement is equal to 0.6 volt, not greater.
Oh, it's the same thing. It has to be above 0.7 volts, essentially. I don't think equals is quite the accurate way of writing it. It should be greater. So Vn. So what's the largest voltage Vn can be? VCC. Yeah. So So Vin must be less than, because the trick to this is it's fundamentally an inequality. So if I sub something in on Vin, it has to be a value which is less than, right? Because the equality itself is less than. So Vin has to be less than or equal to the power supply.
I think it says in the question, the transistor base voltage is in the range.
No, so the problem is the question just states that Vn has to be greater than 0. It doesn't say anything about VCC. It says VB has to be less than VCC, which I guess then you can infer that the largest voltage available, because you have to imagine that this system is constrained. You can only use voltages available. The highest voltage we have access to is 3.3 volts, right? That's VCC. So if I sub in, and again, I'm just looking at it from an inequality perspective. If Vout is less than or equal to Vin, if I can then figure out what Vin is less than, I can write this as less than or equal to VCC minus 0.6 volts, which gives 1.9 volts. So this would give you, this value is lower than the value up, so this would be the proper bound. Okay? So this probably is a little uncomfortable, but yeah. Was that any questions? Okay. So then the lower bound is very simple, thankfully, because we just discussed that VBE has no impact. So then we just say, therefore, VCE is greater than or equal to Vout minus. So we're looking at this VCE. So we say Vout minus what's the emitter at? Ground. So nothing. So then greater than or equal to 0.2 volts. So then we have a lower bound. So this is my lower bound, and my upper bound is here. So then you can sub in your upper and lower bound here. Right, like that. The one thing I did miss was that this equation, so these are AC waves, so we need to take the RMS value. It's like the average, right? So I also forgot this when I was doing the question. So this would be √2, right? No. This would be, so instead of 2, it would be √2. Okay, let me just slow this down. So this would be, you take the average of these two, right? Vout max minus Vvent, and then you would divide by 2, and then that would be, and then you convert it to RMS. Yeah. Is that okay so far?
Why is this subtracted by Vout main rather than just taking Vout max to find max power?
Because in power amplifiers, we're looking at the swing across the load voltage, right? Because power is not just dependent on what's happening here, it's also depending on what's happening here. So we're looking at the swing across the load. That's the total power. And then when you do this, you get 7.22 milliamps. Okay. Any questions? Okay. Very last question. This question, given the time, I'm just going to talk about it rather than go through any calculations. So the amplitude of the load voltage must be at least 650 millivolts. More than 75% of the battery power is being dissipated in the power amplifier when it is active. Thus, a more power-efficient Class AB power amplifier should be considered. Discuss any design challenges there are in implementing a Class AB amplifier in the system. Any thoughts? So instead of using Class A, we use Class AB instead. Maybe let me just draw it so you can see what it looks like. So Class AB used a constant current source. Class A used the current source. In Class AB, we have, what does it look like? We have like this. V1, V2. Ground. And this is VCC. So that's RL. Now, what we can see the difference is clearly is now rather than just having a base voltage, now you have two input voltages. So V in 1 and V in 2. So the bottom transistor is no longer a current source, it's an actual power transistor. So one of the transistors handles the positive portion, one of them handles the negative portion. And we can assume it's being biased to be class AB. Any ideas as to why this is difficult to implement in this system? And the hint I'll give, and you can kind of infer the hint from the previous question, is it's got something to do with the limits of the amplifier. And there are calculations you might have to do, but I'll probably just skip them. Any ideas? So now with this in mind, I'll scroll back up. So maybe just look at what's changed between the two. So what's the difference? Yeah, VBE is no longer constant. Right? You're just looking at it. Now the transistor at the bottom actually really matters because VBE is not constant. And so when you recalculate the range required, so when you calculate the maximum possible voltage you can get from this, so you go through the similar procedure we just went through, right? The exact same procedure. You get that the range is, so V out must be less than, or equal to 0.6 volts, and V out must also be greater than or equal to 1.9 volts. And when you go through the same power calculation, I just calculate, and I should mention, these values I calculated, also done by Torsten in the solution, these are best case values. Before we weren't really calculating best case. These were calculated such that we calculated the best possible voltage swing, the largest possible range.
It's smaller and greater.
Oh, yes. Good point. So it should be greater than, should be less than. Thank you. And so when you calculate this value, what you find is that the amplitude, or the swing, because it mentioned we needed 650 millivolts, I could just reach 650 millivolts. I could only just. And this is best case voltage swing. And what's the problem with this? So I've just calculated that, well, I didn't calculate, I wrote down the best possible voltage swing for this BJT, and we found that the best case is it reaches 650 millivolts, exactly on dot. But to reach this assumption, yeah, so that's pretty much it, right? So V in, it requires V in to reach VCC. Is this practical? Is it practical? So it requires the input to be able to swing to VCC. Impractical, why? Wouldn't be biased?
Like it wouldn't be the forward active transistor. I mean, the collector has to be more positive than the base.
So you're saying, so V in can't swing to VCC because it has to be more positive than what, sorry?
So like VCC at V would be equal to like transistor will.
So there's no condition on this transistor really. So sorry, on this side from here to here. The conditions are really from here to here, and so the ranges have been calculated assuming the transistor stays on.
Is it so that we can keep V in within certain margins of the
Yeah, that's pretty much it, right? So we have to, this is really a practical problem. We have to keep it within margins of VCC, and so really you'd have to have access to some sort of internal supply voltage. Like VCC int. So this is an internal supply voltage which is greater than the supply voltage of the output, right? And this is just so we have that margin, right? Purely that's it, just so we have a margin on VCC. Yeah, I don't think there's anything else to it. Like an internal VCC. You'd have to have access to some internal voltage that's greater than VCC. So, because, one way of thinking about it is we just reached 650 millivolts. Just. But in reality, it's not going to reach 650 millivolts. It's going to reach like 620 millivolts. So we need even more voltage, but at most I have VCC, right? But we need more than VCC. Now, Torsten also provides another possible argument to this, which is probably a bit confusing, so I'll just quickly explain it. He mentions, instead of using BJTs, because what was limiting our voltage swing was, what was limiting our voltage swing? The BJT, right? We just have to keep the transistors on. So if I can have a way to reduce, so this voltage and this voltage, so instead of using a BJT, you can just use a MOSFET. A MOSFET has a lower threshold voltage to turn on, right? So a MOSFET, you can just use a MOSFET instead. And unlike a BJT, the threshold voltage of the MOSFET can be varied. So we have designed MOSFETs which have a lower threshold voltage. So this thing here, the reason it's drawn as disconnected is because you have a gate and you have the channel. And sitting in between the gate and the channel is oxide, a layer of oxide. And the thinner we make that layer of oxide, the less gate voltage is needed to communicate with the channel. So it's very easy to adjust the threshold voltage on a MOSFET. And so if we replace the BJTs with MOSFETs, with low threshold voltage MOSFETs, we get a larger voltage swing. Okay. Was there any questions to that? All good? Okay, well, sorry for it taking so long, but I hope that was a bit of a marathon. Any final last questions regarding this, the exam?
I think on previous question, I think you mentioned power in amps.
Oh, did I? Yes, it is most certainly not amps. Check the solutions. Amps, yes, not amps. But yeah, just make sure to take the advice I mentioned at the start as to how to approach the past papers. Biggest piece of text, just skip to the end and see what you need and work backwards. Okay. But yeah, otherwise, thank you for coming. I hope it was useful and good luck with your exam. We can talk after.
Does that mean you should do like the question 2 and 3 if it's relatively short?
No, do question 1 to 3. Do question 1 to 3. Okay. Cool. Thank you guys. Good luck. Yeah. Hey.
See you around.
Yes, yes. Thank you for coming. Thank you. Thank you everyone for attending online. Oh, no worries, last. See you. Thank you for attending. No worries, my pleasure. Do we just turn off the stream?
Announce yourself. Just like make sure your name's in there somewhere.
Oh, okay. Yes, I already announced myself at the start.
Really?
Yeah. Okay. Otto would like me to re-announce myself. My name is Hassan, and I hope you had a great time.
Hey.
Cool. Thank you, guys. Best of luck.
Fantastic.
Thank you. Thank you.
And end it.
See you guys. Cheers. Is that over?